We say, "What's up, YouTube?" Okay, all right. We said, "What's up, YouTube?" That's the first most important thing. We verify. Okay, I don't think it caught the "What's up, YouTube." I might have to do another one later. Okay. There's no way it's week A. Oh, it's week B, and I didn't update the numbering. Right, it has to be week A because there's only 14 weeks, and we only have 2 left after tonight.
It's 14.
A 0 indexed. Oh wait, are we thinking there's an extra week? Did I? Oh, I counted spring break.
We don't possibly because they have to be slots, like
Yeah, I wasn't billing you for that one. Okay, let's count them real quick. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, we did a. Oh, no, I counted spring break. 10. 1, 2, 3, 4. Yeah. And you gotta count them because sometimes I like use numbers twice and stuff, right? This isn't auto generated. This is actually a work of art.
you haven't figured out a way to do like a CS like an HTML list element that numbers hexadecimally. Yeah.
I was like halfway through figuring it out, and I was so tired already. It's just like there's you can see there's one other thing that's bothering me though, which is that I was trying to get all of this information into 6 characters. But you can do it, right? You prefix with the decimal day of month, and then you do the 3 character month code, and then you suffix with the single hexadecimal digit. But I don't think anyone would understand what they were looking at if the first week said 13 Jan 0. So I didn't do it, but I'm going to change it as soon as the semester's over. So full screen. And
You can do 2-digit years,
I can do
2-digit years. Like 250124.
25, 2501. I can't think about that right now. You've completely bamboozled. Yeah. Yeah. Oh, yeah. I've got another one I've been using for years. Doesn't bother me at all. I love it. It makes me feel alive. It's the best feeling I can get short of using Linux. Okay. um. Oh, I should say where we're at in the class. Okay. So I think I basically taught you cryptography. We can debate the merits of whether that happened or not. Separately, I think I talked to you a little bit about Podman. The feedback I'm getting from the students that understand Podman is that I did not successfully teach anyone Podman. So I guess I don't really care what they think. I think I'm like pretty sure I taught you Podman. I will say I've walked around the classes a few times and have not seen anyone use Podman successfully ever, right? So if it has happened, I haven't seen it. But really, I just wanted you to be aware of containers, and it solved a few problems with the auto graders early on. Some of you may have noticed on the list T assignment, there's not a containerized auto grader. That is by design. The first students have started to use other systems languages for that, and that's totally okay. That was intended so that an interested student could do a solution in C++, and it has actually been used for interested students to do the solution in Rust. But you are totally unrestricted on list T. The only thing you have to do is satisfy the auto. It would be a little gross to write a wrapper around Python since I'm asking you to implement the Python lists, but in a way that would be cool, right? So, okay. So what we're going to do data structures in general, and then we're going to do a specific data structure, and that data structure is going to be the blockchain. The blockchain is a little bit weird because it's kind of more than one data structure, so we're mostly going to talk about the chain part and the block part this week. One of the entries in the block part is a tree, which is another data structure, so that's the data structure we're doing next week with graphs. When I first got into this program, my impression and this was the MSDS, but close enough, right? If we squint, there should have been a course called Sets, Graphs, Automata. And I'm arguing we've basically done sets by doing number theory, which is sort of applied set theory. This week and next week we're doing graphs, and then the last week we're doing automata. And so sets, graphs, and automata are not the focus of this course, but I sort of jammed them all into these last 4 weeks along with everything else going on. Sort of the central conceit of this cryptography course is that you can teach these large numbers of things at the same time without anyone noticing. And so that's kind of going on. Anyways, we're going to introduce data structure and see. These slides, you should all be learned. They contain something that is very scary to a lot of people. I have Java code on one slide today. So if you see Java code on the slides today, do not be alarmed. I put it there. I wrote it, I debugged it, I tested it, and I did it all inside a container, so there wasn't a Java runtime on my local device, right? So I was safe. Containerization protected me. Now that I know about containers, I can use Java. That's kind of cool, right? Because I was unwilling to install it. So if you see Java today, just be cool, right? It can detect motion. So I'm going to motivate data structures. I'm not going to motivate sets, graphs, and automata. I'm going to motivate data structures. There's 2 terms that I have to use to cover the bonus content today, and then I should introduce as vocabulary words regardless. I'm going to teach you about the C language struct, and I'm going to just have a few comments on what I think the usefulness of teaching struct is. And then we're going to talk about typedef, which is just sort of a useful macro. If we get through all of that, we're going to talk a little bit more about header files. I'm going to set the cutoff on this slide deck for probably a little bit after 8, which is usually when we've been going to the second set. Yeah. Are there any questions about anything? How's everyone doing? Are you listless or are you listful? You're listless? Okay. All right. Well, so this slide is named after Normani's debut single, Motivation, which I'm sure we all remember. Okay. So, you know I'm opinion gifted. I was gifted many opinions when I was small. And one of my gifted opinions is that this is bad. This is the data clump anti-pattern. Talked a little bit about anti-patterns last week. And then we showed a few ways to get around this with various sorts of things like mallocs. The most obvious way to get around this is with a void double star. But void double stars come with other consequences. For example, what the heck is a void double star, right? Is like a very obvious thing to ask if you ever see one of them. It's like, why is this a pointer to something that you don't know what it is, right? That seems like a strange way to solve problems. So instead of solving problems that way, we're going to say exactly what it is. This is how we addressed the problem with malloc. So here's our void double star. And what I want to show you here is how annoying this is, and also how few of these lines of code are interesting. So this is just a variable declaration, and in fact, I don't actually have to do a malloc here. I want to pop this up and try and live code a bit. Okay, so we're going to work with malloc a little bit right here. Ooh, I should make sure my sound and everything's working. The sound is working. Okay. Okay. So how are we going to do this? We're going to pass the arg around. So we're going to vim arg test. I don't know. Windows don't work when things are full screen apt. Okay. Function F11. All the keybinds are different on my new computer. Okay. Include standard io.h. I'm going to, as convention, use an int main with an int arg and a char ** arg. Okay. Now, in line 2 on the slides, I use a malloc. I'm not going to use a malloc here. I'm going to create a void star buffer, and it is going to look quite similar. So I'm going to call this void star arg S for struct or for multiples of it, so the plural, and that's going to be of size 2. What is this thing? Okay, so this is an array of length 2. I've also called them buffers, and I have uncommonly called them vectors, but it is reasonable to call them vectors. So I have 2 of something. What are the things which I have 2 of? I have 2 void stars. How big are void stars? Void stars are of size 8. This is 16 bytes. I'm going to put 16 bytes of information in here. Well, actually, I'm not. I'm going to put 12 bytes of information in here, and I'm going to use 16 bytes to store it. Okay? Then I'm going to, I should have called it both. That's what I called it on the other slides. We'll change this to both. Okay. This is similar to the malloc. What is the difference? That malloc grabs 16 bytes on the heap. This buffer grabs 16 bytes on the stack. That's all. Okay. Then we're going to say both 0. This is directly at location both. Directly at location both is the 0th indexed byte, which is some location on the stack. In general, I should expect it to be 16 locations ahead of where I am on the stack because I asked for a 16 byte chunk, and now I'm going to go back to the top of that. Now, what am I going to put there? Well, I'm going to take argc, and I'm going to cast it to be a void star. And I'm going to store it inside both. Now, what does that cast do? Argc is an integer. I don't know how big integers are, and I don't know how big void stars are, but I'm assuming void stars are of size 8 and integers are of size 4. I am also assuming that when the C language was implemented, they were both of size 2, or perhaps 1. I don't know for sure. So I'm going to put these casts in here to make sure no matter what computer this runs on, we have the sizes correctly. What I think is going to happen is that argc is going to be 4 bytes of information. I also think it is going to be a single-digit number because I think I'm not going to provide that many arguments, right? There's not really a cap on how many arguments I can provide, but I'm not expecting to provide that many of them. So I think that's going to be a small number, which means I think all of the information is going to be in the first byte. Remember the example when I added 10 to the first byte and it changed the character H to R in the string HI exclamation point null terminator. So I'm only going to be altering the first byte. Now, if I have 4 bytes and I only have 1 byte that is non-zero, I can just put that in something that is of size 8 bytes and still just have the first byte be non-zero. That's totally fine. I'm wasting space, but I'm not losing any information. Now, when this really gets complicated is if I happen to provide 256 arguments to something, which means it doesn't fit in an 8-bit integer, and I'm working on an 8-bit system, so addresses are only 8 bits, then I have an overflow. So that's very bad, and that could happen. But this, to me, looks legal. Okay, what's the next thing I'm going to do? I'm going to take both 1, and I'm going to set it equal to be a void star casted arg. So this is why both has to be of type void star. I'm going to package up some information and also another pointer as void stars. If I have 2 void stars in an array, then the first element of that array is described as the location of a void star. The location of a void star is either a void double star or a void star array. Then we're going to print arg on both and return 0. Now, I have called print arg here, which means I need to define, emphasis define, the function ahead of that. So we'll do a quick print arg. Arg is going to accept a void double star both. And it is essentially going to copy or duplicate the duplication anti-pattern, the work that I did in main. The same way I packaged things up to put them in both, I'm going to extract them from both. So how I'm going to do this, I'm going to create an int argc, which is going to equal to an int cast of both 0. I'm going to create a character star argv, which is going to be a character star cast of both 1. I'm not going to do anything in particularly fancy here, so for the sake of this example, I'm just going to print the first argument, which is, and I'm going to give it a new line, which is argv0. I'm going to do an empty return, and then I'm going to close that. These lines and these lines have no executable code. Nothing of interest is happening there. That is only labeling things. That is only telling the compiler how to think of things. So not only does no computation happen, but also they cancel each other out. This is very bad. I think this code works. Let's go ahead and exit way up. You never know what mode you're in Vim, especially if you're teaching a class, because you start talking and you start. Okay, so we're going to gec arg test. And there it is. And we can change the name of it. Oops, what I meant was, there we go. Look at all those warnings went away. And we can get not name. Right. Okay. Okay. This is the same thing I just wrote. We can accept both as a void double star. And then this code works as expected. This is a way to print everything. You'll see here I just have a simple loop that loops over argc. Nothing too complicated. Okay? So this is one way to work with data structures. Now, you already have worked with data structures because 496T was a data structure. It was the array data structure. We passed around arrays of 64 integers of size 64, or perhaps you implemented it differently, right? Perhaps you used 128 integers of size 32. That's totally fine. Perhaps you did things word level or byte level and passed around whatever 496 divided by 8 is, which I guess is 512. So maybe you had 512 uint 8Ts. That's completely fine. That would be a very good way to pass around string data, for example, right? We remember at some points in time, especially when we were doing encryption, I would type something into my computer, say, dear computer, this is actually a 496-bit integer. Please perform a division on this, and it would work, right? So you have already worked with data structures. I tricked you. You've been bamboozled. You've already used a data structure, but you've used linear data structures of a fixed size. And we're going to progress past that. And we're also going to get past just referring to things as pointers of some kind, which is somewhat unsavory. Okay? So that's what we're doing today. We're doing structs and type def. Okay. So now we introduce the stack and the heap. One of the reasons I popped open what I call this thing, arg test. One of the reasons I popped this open is I wanted to show you. You have the example on the slides, and now you have the example in front of you, and it is recorded. This is the stack allocated both. Let's see. Where's heap allocated both? There we go. There's heap allocated both. Not great, right? I don't know if it's necessary to argue in either direction for a design decision, but I did want to show you this pattern again, which is malloc, size of how many you need times that size, a cast, and storing it inside of a variable. So all of that works well. Okay, so we've created argc and argv on the stack. Well, they're actually already on the stack. They were given to us on the stack. The operating system provided them to us as a stack, or perhaps shell. And maybe we don't really want to differentiate between shell and the operating system. They're quite similar, right? So when main starts running, argc and argv are already on the stack. They have to be somewhere. So we're going to pop them off of the stack and start loading them into this data structure, right? And we can do that whether the data structure is on the stack or the heap. Okay. We're going to store argc inside the first argument, argv in the second, and then break. Okay. Now, when we do this, at this interplay between the two of them, what's going on here is both is being pushed onto the stack. And what is both? In this example, both is an 8-byte description of a heap location. That's what it is. In this example, both is a different size. It is a 16-byte array. Somehow this is going to work, and the way that's going to work is because the first location in that 16-byte array happens to be the location of the other 16 bytes. So it's totally fine when we call the function, right? Okay. We're going to call this on both, or on both, right? And we're still just giving the location of a void star, right? And that location can be on the stack or the heap, no one cares. Okay. We're going to pop both, the thing called both, off the stack, but we don't know what it is. And this is annoying because then whoever is writing argv has to know what is inside both, and it has to not be some other kind of void double star. So, blah, 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 we do all of this stuff. Okay. What I would like to do is I would like to have a way to document for GCC, for clients of my code, for everyone else, what type of thing both should be. I need to describe it, and I still want it to be just one argument, right? And this is, I think, what should have happened to main in C. And so we're going to do an alternative to just using void stars for everything. I think I'm still going to waste those 4 bytes, not bits. But I don't think I'm going to get warnings anymore. So you'll all remember I was hiding this from us, right? But this pointer to integer cast is not a good thing. We don't want to be doing that because it's potentially unsafe, right? And this is my proposed solution. We're going to use something called a struct. Struct is one of the few reserved special keywords in C. We've seen other reserved special keywords. We've seen if, for, while, do while. Maybe we've seen go to, right? Struct is one of them. Struct to me is less similar to if, for, do while, and go to than it is perhaps to Python lang class or def. But as with those other keywords, it has somewhat the same structure. We have the keyword, we have something else, and then we have a code block. How is it different? Well, with an if, the something else in between the keyword and the code block, this would be an expression that evaluates to true or false. We're not using an expression here. We're treating this much more similarly to a variable declaration. So that is the name of something. We are giving the name of a type or the name of a function. It is possible to have multiple instances of this struct. So this is a little bit different than the other things we've worked with so far. Much closer to classes in object-oriented programming. We open our code block. And as I mentioned, we open our code block, I'm also going to mention that we are going to terminate this code block with a semicolon. This is an incomplete sentence. It needs punctuation. It is not like functions in that sense. It is much more similar to variable declarations, and variable declarations are semicolon terminated, right? Okay. Inside this struct, we're going to have argc and argv. What else? And this is the things it is. Semicolon terminated, named, code block, contains only variable declarations. We note this contains no executable code, but I've already talked about how much we can do without having executable code, right? These 4 lines contain nothing happens in them. All of those are just telling the compiler things are going to happen. This line, this one matters a lot, right? That reserves space on the stack. That's very important, right? So not every declaration doesn't matter, but these ones don't do anything until we use them for something else. Okay. That's the motivation. In order to treat this more clearly, I'm going to introduce 2 terms, and I've been trying to use them correctly throughout the course of this class, and they are define and declare. Generally speaking, when we declare something, we are saving an idea for later. We are going to call it later. We are going to use it later. We are putting the compiler in a position where it understands what we mean when we say something. This is programming. This is the sort of the stored memory program. This is a way of describing bits and bytes in memory that are going to hang around. The most common thing I think of as declaring is the names of functions. And I'm going to do an example of declaring a name of a function separately from describing it with our running example right now. So I'm going to come back over to command line. Let's see. I want to yoink. Is that 6 lines? Oh, I wanted to cut them, not copy them. What does anyone know the cut command in Vim? Is it X? D. Oh, it's the same as delete. Okay. So whenever I've been deleting things, I've actually just been cutting them. That's how you can undo deletion so easily. It just goes in some buffer somewhere. Okay. So we're gonna do D6J. Then we're going to do probably 8J. Okay. And then we're going to paste. Okay. Oh, that's too far. Oh, I'm not in insert mode. Okay. Okay. Take a look at this. Okay. We're going to gec arg test. And we're getting a new warning, which is the implicit function declaration. There is a function that is being used before it is defined. This function right here is used before it is defined or declared. Or, yeah, it is an implicit declaration, right? Let's go ahead and run this and see what happens. Still works. That's kind of cool. I was kind of expecting it to break, but that's fine. We still got a warning. We're now going to fix the warning. And we're going to fix the warning with a declaration. We've seen declarations before, predominantly in header files, but we can also do one directly in a C file. I'm going to declare void print arg void star both. Now, this is a declaration, not a definition. I'm only saying that something is going to happen, which means it's not a complete sentence on its own. I have to semicolon terminate it. This is the same thing as declaring a variable that is later going to take on some value. It is only down here when I define the value with some code block that I have a complete sentence and don't need to be semicolon terminated. Gec. And my warnings went away. The implicit function declaration warning went away. So this is one way you can sort of sequence break your various functions in C programming languages. Some of you may have tried at some point to have written a mutually recursive function. An early version of my division function had a helper function that it called and then also called back into division, which meant I had to declare one of them in advance, right? Fortunately for me, I was working in 496T, which had included 496T.h, so big div was already defined. So I just put the helper function first, and it could refer to the declaration in the header file, and then it would come down later to the .c file. So that is one use case for the split define declare differentiation. When we declare something, it contains no executable code, and I can show you that. Nothing in here is executing. There's no times, there's no multiply, there's no divide, there's no return statements, there's no mallocs, there's no prints. It's just the name of something, right? This is in contrast to definition. Definition is often used with variables via single equals assignment. And in a really cool language, and I actually love this about R, one of my favorite things about R is it does arrow assignment. I almost always want to be defining things at the end of expressions instead of at the beginning, and you can do that with the arrows, which I really like. So I usually, in the languages I write oftenly, I refer to it as single equals assignment. My impression has been the more times I say single equals assignment and double equals comparison, the fewer mistakes I see in students writing. And now I'm wondering, is that actually because the students are listening to me, or I started saying that and stopped making errors, and then people stopped copying my errors? And I don't know which one. So anyways, I became a single equals assignment saying truther in the past couple of years, and I'm encouraging you to do that as well. It's easier to think it. I think if you say single equals assignment out loud, everyone thinks you're kind of weird. So maybe just like keep it to yourself, but I don't know. It's good to keep track of. Okay. Oftentimes we do this with single equals assignment for values, but we also do it just with these parenthesized, or I don't They're curly brace enclosed code blocks, right? And in fact, we can also use curly brace enclosed arrays. I don't know that we want to see this, but I think no one can stop me from. Wait, no, that's an argument. Let's do something up here. Okay. I think. Well, no. Let's do this. I have a. So that's also defining a variable with a code block. The code block is just two values. And I think if I compile this, it's going to work. So, this curly braced code block thing, sometimes they contain executable code, sometimes they don't, right? In the case of structures, they don't. With inside the code blocks, depending on the type of code block, if it is a structure or an array, it may only contain, for structures, the names of values, and for arrays, the values of values without their names. And for functions, it may contain executable code, including plus, minus, times, other function calls, other definitions, right? And in fact, I think you can even declare a structure inside a function, only use it inside that function return, and then it will never bother anyone else, right? So we can do all of these things here. In GCC C, you are able to define functions inside of other functions, and that is not allowed in standard C. So the C89 flag will break that. But I didn't know that when I started writing C, so I wrote a bunch of nested functions. Here's just the differences between what I mean when I say declare. Declare allocates some bits. When I declare a function, that function's name has to be maintained somewhere, and it has to be accessible to running code, right? So void sumfunc, essentially what that is going to store is it's going to store a function pointer. It is going to describe the location of where the function is. We can only store function pointers because we don't know how big functions are. So sumfunc is a pointer that refers to a function. And with functions, the pointer non-pointer thing is very, very, so we just try not to think about it, right? But on the stack somewhere, there are 8 bytes that refer to the location of sumfunc, right? Okay. Then we have an integer I. On the stack somewhere, there are 4 bytes that refer to the numerical value of I. My shins are tired. It got hard to stand up. What is going on? Yeah. I think that's what a weakling would use. Okay. Yeah. So what's your question? Oh, it made it dramatically easier to write compilers. So think of it this way. I give you the assignment to write GCC, right? One of the first things you might wish you could do is every time you see a function, you know how much working memory it needs. And so if you say, there are 4 integers and a character star, then you know how much memory you need. And it was way easier to implement. In between 1989 and 1999, people got really, really good at writing compilers, and they just didn't care anymore. I have advocated using C89 instructionally for 2 reasons. I think it is very difficult with modern computers to entice students into thinking about how many bits they use. And I think you really should do this if you end up in an embedded space. The example is always like the space shuttle. Every bit you lift into orbit costs money, right? So you use fewer bits, right? And I do think memory management matters and is undertaught, so I restrict to C89 for that reason. And then the second thing is, someday you may wish to write a compiler. I am planning on teaching a compilers course someday to someone, probably not to you, right? But having taught C89 makes it much easier to write the C89 compiler as a student project, right? Every year, a small number of students go off and write a compiler for the language they learned that year. And I thought that was worthwhile. So yeah, a lot of the C89 stuff is just being pedantic and forcing you to write code in a certain way to like cultivate that practice, right? But when we think back to like how hard how hard were things and what was hard in 1989. And one of the things that was dramatically harder was knowing how much memory you had to work with. Um, Something that has often resonated with various students is, I guess, Mario, Super Mario Brothers 3 on the Nintendo Entertainment System was maybe like an 8-bit game or something. And I played that growing up, so that was extant in my lifetime. Um, and I thought a lot of the speedrunning tricks on that are like causing values that are too big to be written into certain places or something, right? So this notion of like, I remember using computers where it mattered a lot if they knew how much memory they had. And I don't think like undergrads right now have that experience. I don't know how old any of you are, so I don't know what experiences you've had, right? But the generation of programmers that knew how to think about that stuff is going extinct, but the skill is still useful. So that's always been my analysis. But yeah, good question. I think it's so interesting that, and I don't think there's a lot of other things like this. So fundamentally, you can't have a function return a function in C because it's impossible, right? That's why it's not allowed, right? But like they required you to write variables first because it was easier for them, right? Just like totally different reasonings for these two things, right? Um, and I would argue that C++ has come along now, right? But like for me, there is no like acceptable way to implement classes and objects in C. And that's why they needed a whole other language for it. And that language cannot be used to write operating systems. It's a little too squirrely, right? And so like that's an example of a change that made to the language that wasn't possible, right? So there's impossible things that have been changed as well. Okay, that's the vocabulary. Structs. Okay. In many object-oriented languages, classes are used to implement data structures. Okay, so many of you have Professor Lucas Cordova for SQL, data engineering, right? Professor Lucas Cordova became responsible for our undergraduate data structures class somewhat recently, which is our second semester class where you implement data structures in Python. And he's quite frustrated with this because his perception, I think coming from a .NET C# background, is he's frustrated that Python doesn't have strong typing. I get that, right? I'm going to teach you about data structures today, and I am literally only going to talk about how big things are, right? And in Python, integers don't have a size. They just don't. An integer in Python is a data structure, right? So when you start putting integers inside your data structures, that's a recursive data structure, right? I had the completely different opinion when I was teaching data structures before him, which is that I said, the thing I don't like about teaching data structures in Python is there's no structures in it because everything was in a class. To me, a data structure can only be structured data. It must not contain executable code. And in a Python data structures class, by convention, and this makes both the software engineers, Professor Lucas Cordova, and the computer scientist, myself, angry, but we still teach Python because it's so blasted good at everything. When you make a class in Python, it is almost impossible to prevent there from being any code in there. And what is the example? Okay, so if I create a class, why did I start writing my name? Sure. I wrote nothing in there, right? And it contains a function. It is impossible to take executable code out of classes in Python, to my knowledge. And there's also the Python constructor. Let's see. which is a dunder method. No, it's not an it. There's also a constructor other than an initializer. Oh, new. Right. Okay. That's also in there, right? There's at least two methods, no matter what you do. And I think, I mean, I don't know if it has a built-in string. Yeah, right. Like there's a lot of stuff in here. Ooh. Oh, it has no add. Does it have hash? Yeah. Okay. So for some reason the class I made that has no code in it has a hashing function inside of it, right? That seemed a little weird to me, right? I was like, maybe we should throw this out and start over. And so then I started teaching this class, right? Yeah. Okay. And separately, putting on my Professor Lucas Cordova hat. None of those things have types. We don't know how big any of them are. We don't know what they return. We don't know if they return, right? Um, it is completely reasonable, and Python doesn't do this, that actually the repr method should actually just print something and return nothing. It doesn't do that, right? Um, yeah, returns a string, right? But it could have printed and returned nothing, right? And I bet I can actually overload it. I'm gonna stop doing object oriented programming, right? Like that seems reasonable. Okay, let's get me back on task. Okay, um, okay. So I thought the indentation here is wrong, right? That should be indented one more. Um, to me, once you start putting, I mean, methods, but functions inside of something, what you've actually created is a .c file, which we don't really have a word for, right? But that looks an awful lot like a Python module to me, right? And I've suggested actually perhaps we should call these things computation structures, right? That we should not call them data structures because they're predominantly doing computation. And in fact, in the case of class Calvin, which I just showed you, it only contained computation. It contained no data, unless we argue that the functions are data. And that's like a weird thing to start arguing, right? But I would be willing to do that if we want to do that, right? Okay. Um, Here is everyone's favorite example of, or probably, I don't know if any of you took like an object-oriented class, but one of the first things I always do is an ordered pair, right? Why do we have an ordered pair? Oh, well, one of the most natural things to do as soon as you start learning about data structures is, well, I have a lot of times I want to pass two different things around, right? Perhaps I have the number of arguments and also a vector of arguments, right? So this is a pair. This is a generalized way to pass things around, right? Um, Classes allegedly have uses. I must have been like really unhappy when I was writing these slides. I'm much sassier than normal. I don't even know that I think that. Yeah, I just kind of papered over that. I didn't realize that like in lesser languages, classes allegedly. Um, I'm gonna go back and forth. This is not even a complete definition of an ordered pair, right? Um, and this is what I think of as an ordered pair. Why is that? In seventh grade, when I first heard the term ordered pair, it described the location in an XY coordinate plane, a two-dimensional plane. And the way we described it was with two numbers, and we did not describe it with functions. So to me, an ordered pair, a numerical ordered pair, is a location in R2, the real numbers, across the real numbers, Cartesian product of the real numbers, if you want to go there. And it certainly does not contain plus times representation, string, init, new, hash, these other things, right? I've always thought of it that way. To me, it's been easier to think of it this way. One of the reasons I think it is reasonable for me to think this is that the extremely high performance code, the operating systems, are written in languages like this. Because when you are using structures in high performance environments, you care a lot about how much garbage they're carrying around. That is 8 bytes. I know that's 8 bytes. And I can prove it's 8 bytes. Let's get out of the lesser language. I feel better already. Okay. I mean, both things can be. It contains multitudes, right? Does this look allowed to you? I was like, there is a semicolon. You need two of them. I lost my single line permissions by missing the semicolon, so I gotta go back. Okay, I'm missing a bracket. Where's the bracket missing? It wasn't done yet. God, read my mind. Okay. I suspect size of is going to return an LD, and I'm about to write size of. Okay. I did not check this. Struct ordered chair. I want to put a semicolon there so bad, but I actually have to close the outer parens and then do the semicolon. But like, it was like the call of the void. It was like, what the semicolon? What the semicolon? And I know what you're thinking. You're thinking, why are you including the entire standard IO library just to see the size of one thing? And you're right. Let's get rid of that. And instead of printf, why don't we just return this and then we'll view it with echo. Did I really write snooked? What's a snooked? No. Okay. GCC pair.c. A.out. Ah, no, I forgot to say I was going to eat my hat unless it's 8. And then it was 8, but now I can't say it because we already know it's 8, right? Man, that's so sad. That was a whole lengthy bit I was going to do. I was going to talk about, how I was going to season my hat. Okay. I love that I know how big that thing is. Here's a question. You all like Python, right? I don't. Um, sorry. I don't know. Can I? I have no idea how to figure out how big these things are. I do not know. I don't know if you can. Now, obviously, I could look at the source code that's written in C and figure it out from that, right? But short of that, I don't actually know how I'd figure this out. Is there a size of it in Python? Well, wait, no, hold on. I feel like a bit of a narcissist naming that after myself when it was literally just a typo. Okay. There's no way this works, right? Oh, okay, wait, okay, we got it. Okay, import sys. We'll use this ordered pair. Or is this reasonable? Okay. Wow, it worked. That's never happened to me before. Okay. Ordered pair. And what are our two favorite numbers? Obviously, 0 and 1. Those are the only two numbers. Remember finitism, right? Okay. Sys dot. I bet it was get size of. No, I have to check. No spaces. I would. Yep. Get size of. That is absolutely 100% a wrapper around a C function, right? It's in sys, which sys has argc and argv in it, right? So that this sys is just the C namespace. Okay. All right. So this is doing what I said it would do. It's 56. Okay. Let's make a smaller one. Huh?
Of course, what else would
Right, yeah, that makes perfect sense. Def init self x y. I'm gonna get rid of stir and repper. Self dot x self dot y equals x y. Okay. I'm gonna see if this changes the size. No, okay. Um, whoa, that's crazy. 400. Okay, the built-ins are the same. Um,
case size? Like,
aren't they the same?
well, get size. Get size. For int 0.
Yeah, yeah, okay. Okay, so if we do get size of 0, I do expect that to. So
Oh yeah.
that makes perfect sense, right? These all the same. Yeah, the size just changes. You know, it's just like your numbers are bigger, so I guess they take up more space. Um, I would humbly suggest that you should not put Python code on the space shuttle. You could you can run it on your GitHub workflows. You can put it in your little containers. You can do it in your cloud application management. I think it's great for machine learning engineering, and it's probably good for regular machine learning. And do not, under any circumstances, put it inside a car that has to move, right? And some people wrote a Python interpreter in Python, which I would assume would be impossible, right? Because I didn't think you could do anything in Python. But like, if you only have to do Python, maybe Python's the right language to do it. Okay. Um, okay. I've seen a few C compilers in my day, but some of them cost money, so I don't have them. MVCC is the one that Microsoft has, Microsoft Visual C compiler. That one costs money, and I guess there's an Intel C compiler that I guess can do some pretty crazy stuff because they know what their hardware does and no one else does. So, okay, that makes sense, right? Um, every compiler I've ever used puts the stuff inside structs in the order that you type it. But I think there's a case you can get it to reorder things. Um, let's look at an example. Oh, I didn't fix this yet. Okay. I'm going to describe what I could do, then I'm going to ask you if you want to see it or not. argc is 4 bytes. argv is 8 bytes. It is easy, I think, to imagine that if you have things of size 8, you want them to be aligned on 8-byte word sizes. So you want the address of something that is an argv to be a multiple of 8. If you make a struct that contains an int and a pointer, it is at least 12 bytes in size, and the next bigger word size than 12 is 16, so you probably want that to be aligned on something of size 16. So you probably give it a memory address that is a multiple of 16, or expect it to have a memory address that is a multiple of 16. Now, if you take something that you expect to have a memory address of size 16, and you put 4 bytes in it first, and the second argument you expect to be at a multiple of 8, then you must waste 4 bytes just the same way we did with void double stars, because you want that 8-byte pointer to be aligned at an 8-byte word boundary. So I expect if I put a 4-byte word, a 4-byte integer, and an 8-byte pointer into the same struct, that I am going to get a 16-byte struct and there's 4 bytes that are not used. And I can check. You want to see it? That's on. Okay, cool. A lot of you don't know this, but secretly, I'm actually just wanting to practice Vim. And it's way harder in front of a live audience. As I was saying, this is a secret. Okay. So let's declare a struct. What's up, YouTube? We said we'd say it again, right? Yeah. Okay. I really should just do monkey type. I don't think I need to practice Vim. Just need to do monkey type. If I do monkey type, the Vim will follow. Okay. Semicolon terminate that. By golly, print arg should probably accept a struct arg struct. And yeah. Struct args. Yeah, struct. And what should it call the struct arg struct? Just call it args, right? Yeah. It's the arg struct, so you would call it args. Okay. We no longer need. Oops. Okay. We're going to make a struct args struct, and we're going to call it args. And then we're going to say args dot argc. We're going to use dot notation, same as the lesser languages. Though in a way, really, I suspect the lesser languages stole that. Let me see, right? Remember when I was using stack and heap, and I was like, I'm going to use object-oriented notation for this. In my mind, I was like, I'm using struct notation. It's not object-oriented at all. This is so cool. Okay. Args.argv equals argv. Okay. Then we'll print. Really? Okay. This is a struct args struct named args. I love that. That's great every time. Okay. Don't need. This is the equivalent of args.arg. Okay. All right, let's check that. Oh, I bet I'm not gonna have any warnings now. Yeah, okay. Both. It's gone. Oh, I could have called it both. Cool. Okay, so that works. Now, let's poke and prod around a little bit at this argv. And the way I'm going to do this first is, well, let's look at some memory locations. What am I doing? We're going to print. Yeah, and I'll do a new line. I'm going to print as a pointer the location of args. And I think that's going to work. Maybe it's not going to work. I don't know. I'm going to try and print it. I'm going to print. Kind of want to do a note. I'll just number them. I'll number them starting with 2. I was like, should I do 0 or 1? And I was like, I can't decide. Okay. We'll do a %p for. Wait, why am I doing this on multiple lines? You all have the power to stop me. Okay. That's right, I forgot I lost my multi-line privileges. args args.arc args.argv. It doesn't fit on one line. This is why I wasn't allowed to do it. That seems wrong. That seems like cheating. Okay. I missed a new line. And I take out all the spaces and then it fits? It's so close. Is there any way I can make this smaller? Yeah, I'll take out some more spaces. Nope. I've got to figure out why I'm pressing shift. Okay. Um, is that seriously printing one for a location? I've completely bamboozled myself. I've never seen this before. Oh no, it's printing the value. Oh, I see what I have to do. Hold on. No, this is funny. Okay, the number of arguments is one. That's the one. I need the location, which is the location of args. I think. What am I doing? Insert mode. Save. Nope. I look at my hand. Oh, I wonder if it's this hand. Okay, so this has the small arrow keys on it. I bet that's what's getting me. Poor craftsperson blames their tools, which is what I'm doing. Okay. Okay, this all makes perfect sense. Um, if I had a struct that is of least size 12, I expect it has to round up to the next power of 2, and I expect that's 16, which means I expect it to appear on multiples of 16 boundaries in the memory space. That is a 0 in hexadecimal. That means it is on a multiple of 16 memory location. Okay? If inside of my structure I have something that is of size 8 bytes, I expect that to be 8 byte aligned. That ends in 0 or 8, so that is 8 byte aligned. Is that everything I need to know? Why? How far is AB 0 from C? AB, so that B is, those things seem far from each other, right? Wonder what happens if I cast this to a character string and print all of the characters. I think I should do it. Okay. So, I will do it. We'll do an int string. That's a little less unsavory, right? Okay. So we're going to create an int star alias that is going to equal the location of args. Okay. I think that's fine. I'm going to also have an int I for I equals 0. I'm putting in extra spaces when you're doing that. I less than 4. I think there's going to be 4 of them. Right. So I think integers are of size 4. I think this thing is of size 16, so I'm going to print 4 integers of information. Okay. We're going to I++, and I'm going to print the integer. I'm just going to use signed for now. The new line, alias, I. That seems fine. Yeah, that looks okay, right? And the way to check to see if that's okay is we need to also do I'm going to include standard int.h because I want something that is exactly 32 and 64 bits in size, right? Both. Okay. Um, so I'm going to use standard int. I'm going to use uint 64t's. And then I'm also going to print oh, these have to be LD. And that has to be 2. Remember when I said don't use magic numbers, and then what I do? I used a bunch of magic numbers. And I had to fix them. Okay. And I'm going to print f the percent %LD new line of the wow. This keyboard is definitely slightly different than what I'm used to because I just hit something by accident there too. That's interesting. Um, you use so many keyboards, right? So I use like probably 3 or 4 on a day like today, right? Each on the different campuses, right? But you're still so used to every single one you use, right? It's remarkable. What I'm going to print here as a long decimal is args.arg. I think. Maybe this will be the same. Got the percent. Okay. We'll tail 10. Okay. The one location in the uint64 array that describes the same data as args is the same as the arg value of args. Arg being the second entry. And even though the first entry is only of size 4 bytes, the second entry starts 8 bytes after it because it is an 8-byte sized entry. Now, this does tell us one other thing, though, which is that they are keeping these things in order. argc is still first, and argv is still second, which we can see as we're printing 1, 2. So there's a 1, and there's the second value, which is, and that's a different looking value because that's describing a memory location. Right? So we print that value, memory location as the 1th location in this array, which is not really an array, treating it like, and that is the same as arg. Now, I think it may be the case that if I put some other value in here that is also of size 4, I don't know where it goes. Because there's 4 unused bytes before argv, which would save space, but I'm not keeping things in order if I use those bytes. So I don't know what happens, so we're going to find out. We need a recognizable number, so we will do probably 1, 2, 3, 2, 1 is like fine. We're going to go up to 3 here. Oh yeah. So what do you think is going to happen? I think it's going to use another 8 too. I think it'll put it at the end. Yeah. But I don't think it's required to. Yeah, it's at the end. And I I will never overcome my demons. Yeah, so then it's using 24 bits to store 16 bits of information, or 24 bytes to store 16 bytes of information. By the way, did they have to call them bits and bytes? Like, the string edit distance between those two things is very, very tiny. They should definitely be called bits and octs, right? And for a while, we almost won for a while because they were called characters and words for a while. And it's like those are actual words, right? Like those mean things. Okay. I think it is up to the compiler, but I've never seen it not put them in order. I don't think you can assume they are in order, but I don't. It's possible with the C89 flag you can assume they're in order. Let's put on maximum optimization. I bet this won't change it, but we have to check. Yeah, still 24. Oh, wait, no. Oh, because I did 0. Okay. Yeah. Um, this is what we just did. Ta-da! Okay. Just like arrays. Um, what is happening internally? Probably. We didn't check. We didn't examine this, but in this code, what I suspect is happening is this is going on the stack inside main. It is getting popped off the stack and put on the stack again at a slightly lower address. Or it's not even getting popped off, right? And so when we call args here, that's probably a copy of args, and it probably copies all 24 bits. But that, all 24 bytes? Characters? Okay. And so then this gets all 24 of them. And we know it gets 24 of them because we know the size of this thing is 24, so we know that this thing is expecting 24 bytes to come over the wire. And someone put a space there, and I don't know who it was, but it's very, very ugly. It's still there. Okay. A style is useless. Okay. The undergraduate entry-level class was designed by Eric Roberts, who is probably in his 80s now. He's currently retired. And he really, really didn't want students to ever store data inside dictionaries because it confused them of the difference between compile time data storage and runtime data storage. And I remember talking to Eric Roberts, I said, this isn't a compiled language. And this was very upsetting to both of us, right? For completely different reasons, I think. So the term that has been floating around in the ether for a while to describe this type of data structures, this is a record data structure. It records information. It does nothing else. Records are dead. They've been killed by JSON. They will never come back. They are still useful for high performance because if you have ever used JSON, you've been thinking, God, I wish this were a binary format, right? That's what do you not all think that? Every single time I use JSON, I'm like, the information density on this is so low, and I'm moving it across the internet, right? Which is slow to begin with, right? So I've never voluntarily used JSON except for my .ipymb files that I use instead of the R project for statistical computation. But it looks like JSON won the war because it's a little bit too nice to move things that are printable. And this is actually the same sort of thesis that's been supported by the base 64 and base 85 coming out. It's just, we would so much rather have things that only contain printable characters because so much stuff just expects there to be printable characters. Even if you're just working locally on one system and you're piping it through the command line, you might want that. Structs are defined at compile time. I was shocked the first time I did this in Python. Let's see, class. I'm going to call this one not Calvin. I had no idea you could do that. And I really don't like that you can do that because to me that's changing the size of something. And actually, hold on. Get get size of size of C. Right, so how much extra stuff can I put in here before its size changes? Can I put more information in here than its size, right? Um so I don't know how classes work. Clearly it's storing a pointer, right? But so I guess not Calvin has to be 7 pointers because it's of size 56. And the pointers are probably mostly two methods. And we guessed what some of the methods are. We found new, init, hash, string, repr. And so we're only missing one or two, right? So we can infer some things about how Python's implemented from doing that, right? But um, as soon as you can do this, you do not have a record type in your language at all, is my position. So there is no possible way to implement a record in Python. Um, I'm assuming you all can imagine what happens if I try to name something that is not currently in a struct in C, which is that the compiler tells you to stop and then doesn't compile your code. Let's check. I can't just launch broadsides onto a. Yeah, error. You can't even compile. So you can't do this at compile time or run. It's just not allowed. And that's a good place to break for dinner. See you all in 30-ish minutes.
Yeah. And how would you guys single weakness on them? Or just like spiral and they get some fan frame. Well, when you get good at that, this person. Yeah, but they think that. Yeah,
All right. Let's do type def. Let's do some header files. Let's do some blockchain. At the end of class today, you'll know why you should put all of your money into crypto, which is that you shouldn't. Okay. So there's once there's you should not put your money in crypto. Okay, no, I'll tell you the same joke I told the undergrads, right? I was like, so there is one way to get rich with crypto, right? Which is you get really big on social media, you launch a meme coin, and you rug pull your followers, right? Okay, I'm not done, right? You invest that money in running for office, and you become the president, right? And then you say you're going to put a bunch of really heavy tariffs on everything, right? And then you take all of the money from your rug pull and you buy stock with it. And then you say you were JK, LOL, right?
Is this your
right? So I was going to do it, right? And then someone else did it first. But also, I also joke that this already happened in Argentina. Like, they're the second country this has happened to. Yeah.
The US instead of a giant curve says you've got a big chainsaw.
Yeah. I mean, like, if they were a television show, I would love them, right? It's like every time Elon Musk comes out, he's like, oh, this is one of my favorite characters. Like, what's he going to do this time? But he's real, right? Okay. Okay. So, we like to have fun in this class, right? And one of the ways we had fun in this class was approximately 400 times I said, struct args, right? Referring to the struct named args struct of the instance of which is called args, right? And that's a silly thing to do, right? That was silly. And the solution is quite simple. It is type def, which stands for type definition. You take your struct, and this is really nice because we're required to use the struct keyword, and we should be required to use the struct keyword. We want to be required to use the struct keyword. We need to say what type things are. So we need to say struct, and then this is why I always put struct at the end of my things that are of type struct, because I'm going to refer to them only once or twice ever in very specific circumstances, including in this type def statement. And then I'm going to do a shorter name here, such as args struct or whatever. I was going to call it args, right? And then I already used args, right? So you can't have args and args, right? Namespace collision, that's against the law, right? So this is, I think, the nice way to do this. And if you don't believe me that it's nice, it fits in one screen, and this one doesn't. Look, this one has a scroll bar at the bottom. And if things have scroll bars, that means they're bad. Did you notice how I hit the scroll bar to go to the next? And there's a scroll bar at the bottom of the slides. Yeah, that's like a meta commentary, right? Okay. This is also how Booleans are commonly implemented. There is, in fact, now something called standard bool, I think. And I don't know. It seems kind of high maintenance to include someone else's Boolean header file when it takes one line to include a standard bool. Okay, what are you going to say?
Is that higher maintenance to include someone else's header file or to use an entire 64 bits to store whatever it's?
We don't know what they're stored in this, but I would not be surprised if they're 64 bits, and my code will be higher performance because they're 64-bit aligned.
Other ones. 8.
I think it's an API and it's implementation dependent. They're saying integer, so they're using. Okay, you're coming for me for using 8. They're using 4 according to them, right? And it's in conflict with the ISO-C standard. Okay, no, it's not. Okay, I don't know what it is. Anyways, standard bool This is AI generated and therefore a lie, but I happen to know that it is true that this was implemented in C99. So I'm pretty sure. Oh, what else are we doing tonight? Okay, let's implement it. Okay. Um, so I guess we should call it non-standard bool. .c. Um, include. I know how to spell include. So that was a test to see if you knew how to spell it. Standard bool dot h int main bool true. Is it lowercase? That looks fine. Okay. So I think that worked. And then you can GCC non-standard bool. Really? I've never actually used the built-in bools before. Expected identifier or
You just define you can have a variable name true.
oh, okay. So what do I call my bool? I can't call it bool. I'll call it. I'm not gonna do that either. We'll call it boolean. I like. Okay. Wait, what? Oh, because I didn't do the equal sign. Sorry, did I say equal sign? I meant single equals assignment. Oh, you're asking about the precedence? We support our strong independent equals in this classroom. A single modifies equals and single equals modifies assignment. This is the precedence. Are you asking if there is a more than one equal assignment? Okay, you might be too clever for us. Oh, I see. Okay, like the single. Yeah, that is funny. That's what we're here for. Um, thank you. Okay. See, if we were only communicating using character buffers, this would have been clear, right? Because these are different things. Okay. Does anyone remember what we were doing? Okay, so that's allowed, right? Is it lowercase? Whoa, that's allowed too? Okay, I didn't think that was going to be allowed. All right. Um, fair enough. I am now contractually obligated to eat my own hat. Wait, no, hold on. I knew that because standard int is also C99. I guess if my position is that you should be required to use standard int no matter what, and because you need it in C89 to make it a good language, and you're not allowed to use standard bool at all because it's not in C89, it's possible those two positions are inconsistent. Now, I'm not going to say they're inconsistent, right? But if you come to the conclusion they're inconsistent, it would be very difficult for me to argue with you. Oh, yeah, let's add some more. Let's okay. Pedantic?
Yeah.
There's the two pedantics. I bet neither one works. Yeah, I think the thing is because standard bool is part of C89, but it's part of C99, but it's written in C89C, so you can include it in C89. Um, right. I was being falsely accused of using 4 bytes to store a single bit, when in fact I demonstrated that the C standard says you're supposed to implement this with integers.
True. True. 8 bytes to source.
That's fine. That seems roughly the same to me. Okay. Um, anyways, that's type def. Any questions? Yeah, yeah, that's so they're the same length. That one was not a typo. um, I've spent the last like 2.5 years browbeating the undergrads into letting me not write e's at the end of false, and they haven't quite broken yet, but they're coming.
It's true and false to be two six-letter long concept names.
Truthy,
Yeah.
falsy.
EY.
Oh. It's also only a string edit distance of 1 from Halsey. Okay. Um, we have a street named Halsey in Portland. I cannot drive on that street without either listening to Gasoline or one of the other ones. Who's the other one I like? Blue.
There's a street named Halsey in New York City, which is a different name.
Oh, really?
Named actually.
Halsey?
Yeah, it's an editor.
Okay.
Very low string distance.
String at a distance of 0, yeah. But so they're not the same string though, because they have a different memory location.
Yeah.
Okay. You all love getter and setter functions, right? Sorry, methods, right? And to demonstrate what fun they are, I'm not going to write these. I have never voluntarily written a getter setter function from the second ChatGPT came out. Because, in fact, there is one thing AI is good for writing object oriented language code. Yeah, I was surprised too. But because it's completely procedurally generatable, it makes sense. And in fact, before people were using AIs to do this, they were writing UML, which was auto coding all of the object oriented languages, right? So, um, anyways, I do not love writing getters and setters. But there are a time and place to write getters and setters, and one particular time and place to do that is in a cryptography class where you're trying to keep things secret, right? So it makes a lot of sense to keep things secret. We'll just do a brief digression on how secret things are in Python. So we'll make a class secret. It contains. Do you have to do a init this way, or can you define it with a lambda? Stick with me here. I have to spell self correctly, probably. Um, we'll just call the secret X. Is it self or this? It's self.x, right? Yeah. Which is also the same thing used for type hints, which everyone loves that. So you can either write lambdas or type hints in Python. Um, which should my secret be? Halsey. Okay. Uh, mm, I guess it's not allowed. But I can say this. No, I can't. Huh. Okay. Class secret. I wonder if they define functions but not methods. So you can define. All right. It's odd that it let me type it, but then I couldn't create things with that initializer. If you figure out what happened there, let me know. I'm curious.
So even if you had, instead of just putting in self.score X as the background function, even if you put self.score X into statics, I don't think it would let you do it.
Inc x equals lambda it shouldn't be of anything here, right? I bet you have to use this one. And you can't do that either. You cannot assign to lambda?
Well, we can do the colon equals of probably work.
Yeah. Yes, okay. We just have to put it in friends. Okay. And then x, inc, x. It's unbound. Do you have to do like global x equals? I don't know how globals work. But it's interesting this is allowed. And it's allowed until it runs. So it's a runtime error, not a define time error, because there's not compile time errors. Init equals lambda self x self x. Cannot use assignment expressions with attribute. Anyways, so in Python, as far as I know, let's get one of these real quick. Self x. And I think this is the version I actually want. You can create a secret. And the secret is not very secret. So by convention, you use the underscore prefix to denote, hey, you're not supposed to mess with this. And that is insufficient, right? You can make things more secret with double underscore. Which like doesn't really work either. And I thought if you did the double underscore inside a method, it did something. S equals secret. What's after I, J? Okay, so when you use double underscore in the initializer, it hides it a little bit more. But I don't think it hides it that much more. I think it's here. So nothing is particularly secure in Python ever. What is the way to make this secure? Well, hopefully this is obvious to you. At generation time, what you should do is you should generate RSA keys. And then you should store the public and private keys, not in plain text, probably base 64, and you should split them up in memory in some procedural way. Then you should RSA sign everything that's meant to be saved as a key, so that neither the key nor the secret is stored in plain text, right? You know how to do all of that stuff. And then if you ever have to add two numbers together, all you have to do is perform several thousand 496-bit divisions. And then you'll get your encoded number back. So that's why people don't keep things secret. But anyways, that's not particularly secret, and it bothers me how not particularly secret that is. So I switched to the good language Java. I warned you, here it is. Look at this gorgeous language. Look at this. You can just say private, and then it is. Now, I did try to install 5 different JDKs over dinner break, and I couldn't get a single one of them to work. But I got this to work in JShell at home on my Windows 10 device, right? And so I did verify that this code works. And in addition to that, I also didn't write it myself. I asked Gemini to write this because Google loves Java, right? It's one of their favorite languages, right? So anyways, here's just 2 side-by-side comparisons of a non-secret pair and a secret pair. And this is a completely useless expression because you can just say p.x and get this thing, right? But over here, it's secret and you can block it. When I taught Java, I used privacy as a form of type checking. So the motivating example I used for this type of class was I did voter registration cards. And in North Carolina, there was something like 5 political parties. So if you go to change a political party and you put in a party that doesn't exist, it just doesn't update. So it was a private field that stored the current party. I did some version of type checking. I checked membership in an enum. And that was sort of a fun way to do things. This is also a good way to implement natural numbers in Python, for example, which doesn't have a built-in natural number type. So those are the kinds of things I've used this for. In practice, when you use this, usually you obscure something when you don't want your clients to know the implementation details of your library because you reserve the right to change the implementation details later. Let me give you an example. Say you're implementing standard bool and you're worried you're going to get bullied for using 4 entire bytes for storing 1 bit of information, right? Maybe you just say, hey, there's these things called booleans, don't worry about what they are. And then if you start getting bullied for your choices, you can just go in and surreptitiously change it from an integer to a character, right? But I bet no one in this classroom would ever bully someone for making that kind of choice, so we don't have to worry about that. Anyways, credit where credit's due. I think there are 2 things Java does well. I think it does public-private very well, which I believe C++ also does. And it also has something in it called interfaces, which are also very good. But all of the things that Java does well, I am now going to teach you in the next 20 minutes. So we love encapsulation. Encapsulation is when we put something inside, usually for me a function, and then we never think about it again. You all remember the Enigma assignment, perhaps? That's a famous undergraduate assignment. Apparently that was meant to teach students classes, which I didn't know. I thought it was meant to teach them lambda expressions, right? Because you can encapsulate all of Enigma in 3 lambda expressions. That's all you need, right? You have the forward encryption, the backward encryption, and the rotate. It's only 3 lambdas, right? And apparently not only were the students not supposed to know this, but like maybe most of the other professors that taught the class didn't know you could do it with 3 lambdas. And so I think we're all just going to process our feelings about that next year and see what happens. I was like, this assignment's great. It teaches you to use lambda expressions. And then I got in a lot of trouble and had to change my instructions to require students to use classes. So then I taught my own class. This is why everyone hates me all the time. Okay, so we love encapsulation. I think a great example of when encapsulation would have been better is in the 496T struct. It should not have been required to implement that with 64-bit integer pointers. You should have been able to implement that with whatever you wanted, right? We didn't have type def yet. We didn't have struct yet. So just treat it this way. But also we'd used arrays in other ways. And in fact, there is the I am always fundamentally protected by the C language convention of argv, where you just like pass someone a double pointer to characters and hope they can figure it out, right? So, and I think, Ari, I believe you pointed out that maybe some of my code assumed endianness in the example big sub that I think I provided, and I don't know if that's actually true or not. But the fact of the matter is, like, I was writing developer notes while I was implementing my stuff, and I went back to it a few weeks later to write big RSA, and there were design decisions I'd made that I didn't remember making that I had to know what I'd done. So I had to debug my own code to start working on it again. That's bad. That's a failure of encapsulation. And big null was one of the examples, but also I just didn't remember whether one was in the 0th indexed or the 63 indexed location, right? So I'm expecting at various points in your life you're going to need private fields. And so I'm going to teach you how they're implemented in C, and you're going to learn 2 things at the same time. You're going to learn how to do them in C, and you're also going to learn some of the history and how they came to be and what their usefulness was, right? So perhaps you already know everything about all of this, and that's okay. So we have our motivation. There's still typos in here. I thought I fixed these. This means that I didn't commit my changes on GitHub. That's supposed to say pair.c. So I'm going to quickly move all of these into exit. We're going to make a little directory called pair. We're going to cd into pair. And we're going to create a client.c, a pair.h, and a pair.c. Now, someday I will figure out how to copy paste, but for now, you can do this little thing here where you just echo, and then you just direct the output of that echo into client.c. And as far as I know, that works. There it is. And then we can do the same thing with pair.h. Oh, I learned something recently. Do you see how there's no terminating new line at the end of this file? There can't be because I copy pasted it and then I started putting the quotes there and they're not on their own line. It looks, oh, so Echo added one, but oh, maybe you have to have a terminating new line at the end of your files in Vim. Anyways, somehow I saved a C file that didn't have a terminating new line at the end, and it worked in GCC, and it didn't work in Clang. The other one, this one, which I don't have installed right now, the slightly faster, newer one, and I had no idea. Because when do you ever successfully save a file without terminating with a new line, right? Like so many editors just throw them at the end or something. So, anyways, I just thought I'd let you know that because I'm thinking about it right now. Every time I find a difference between GCC and Clang, it feels like I like discovered magic or something, right? Like these things are so similar and everyone uses them for everything. And I found like one time I got like an error to pop up unexpectedly. I was like, yes, I found a difference. But no, I actually got something to not compile in Clang that compiled in GCC, and I'd never seen anyone do that before in the modern Clang that is now considered mature, right? But yeah, and it told me exactly what to do. It said, "What is wrong with you? You don't have a new line at the end of this file." And I was like, I didn't know that was required. Um, so presumably there's some line in the C standard somewhere that says, hey, you have to have a new line at the end of all this stuff, which I didn't know. Very cool. Okay, so what's my password? Why did I do this? 0%. Okay, we'll also get pair.c. I'm going to probably embigify my screen and then just go back and forth and assume you're following along looking at all three of the files at once on your laptop if you want, because this is just sort of like a lot of moving parts. Pair.c. Okay. So, client, and that will be GCC pair.h pair.c client.c. Oh, client. Make is not found. There we. That's how long it should take to install things. Is it still going over here? Hey, I finished it. Okay. Um. Okay, that's not too bad. Oh, I lost a bunch of quotes. Okay, vim pair.h. No, that is in pair.c. Okay, vim pair.c. I lost my quotes when I typed through the command line. And then that's going to also be gone in client.c. There it is. Right on. Okay. No. Ah, okay. Cool. Is it? Permission was denied? I'm not used to that. This client. It's not an executable? What'd I do? Okay, vim makefile. Should that not produce an executable? What did I do wrong? Okay. So for some reason I can't have -o client there, right? How do I? Remove client, remove a.out, make. Okay, there we go. Okay, so I made a little thing here. Oh, that's something. Uh, it's like a machine readable header file or something. It's like a little bit faster. It matters more on bigger projects. It's hard to justify. So something like Makefile, like I have definitely used Makefiles that have run for like hours. And it is really easy to understand why you want a good Makefile if it's going to run for hours. And then I did see a job posting somewhere that specified they wanted someone with experience with gmake, which is GNU make, which is the make we have here. But some people use make files on FreeBSD devices. And they have two different makes. They have their own make, which does most of the things in gmake that has some of these extensions, right? Um, so there are people whose jobs it is to write make files, and that seems hard because that's not really programming. That's something else. That's like systems engineering or something. Um, Anyways, it's really hard to my mind to motivate why you should get super into make files when like this is 7 lines of code and then this monstrosity is enormous, right? So yeah, what is that? 9, 2, 8, 7, 17 plus 9. So that's 20. I only have 26 lines of code here, including the make file, right? I understand you don't need a make file for something that small. But also, I do think it's nice that you can just type make. That's cool. So we will do that. Make is not currently doing anything. This is what it is doing. Okay, so this implements the presence of a pair struct and the ability to create a new pair. This initializes the new pair to 0 and returns it, right? It's kind of goofy, I guess. Okay. And then this over here creates a pair, sets it equal to a new pair, updates it to 1, and does 1 and 2. Now, I'm not printing anything here, and I don't feel like I should have to print anything. You should see that if all of this stuff runs without pulling either a compile time or runtime error, I have successfully implemented a ordered pair because I can populate its values, right? So that's what I'm claiming here. Now, there is one thing here that we might not like, which is I have exposed the implementation details of the pair struct. And so we're going to step through a process of not exposing the implementation details of the pair struct. Now, if you are all toiling away in obscurity on list T, you'll notice that this is the exact same file structure. I have a .h file, I have a .c file, and then I have something that runs both of them, right? So that is one reason to step through this example. Okay. Yeah, I got those to work. Okay. Oh, maybe it was the inclusion of the .h. Yeah, doesn't matter. Okay. So the first thing to do is I'm going to imagine that we might want to shift the structure declaration from the .h file to the .c file. Why we want to obscure the structure declaration, we might want to change later, for example, whether those are 4-byte or 8-byte integers. That is a reasonable thing for us to want to change. So let's go about doing that. No, I want to do pair.h first. Okay, so in order to do this, where's my cursor? Okay, I want to cut from the header file these 3 lines. And I think I can do that with a, is it D3 or D4G? That seems fine. So I'm going to save that, and then I'm going to open pair.c. I'm going to paste. And so I have moved the pair struct from the header file to the .c file, as I did on the slides. We're going to save that, and then we're going to make, and it's not going to work. And why isn't it going to work? in C, and in fact in every language, but in C they yell at you. In C you must know the size of every variable you declare. Struct pair, let's go back. Struct pair P at line 3 in client.c does not have a way to infer how large a struct pair is. And in fact, struct pair is not defined or declared anywhere visible to client.c. It sees a reference to a struct pair in pair.h, but it cannot in fact interface with that. So we have to do something else. We have to solve this problem somehow. Here's the size information. So one way to get around this is we might try and use a type def. So let's go ahead and use a type def. We're going to do what? We're going to use a pointer. Why are we going to use a pointer? Every pointer is of the same size. It is of the size of void star. So rather than passing around pairs, we're going to pass around what is called an opaque pointer. You have seen opaque pointers before. An mpz_t from libgmp is an opaque pointer. So we're going to preserve that same thing here. I'm going to implement an opaque pointer, a pointer to something, but we know not what, but the API knows what it is. So we're going to implement that. Let's go ahead and do that. I think I'm going to edit first pair.h, and I'm going to add a type def. Type def struct pair. I'm going to call it a pair t. Semicolon that. My impression is that noop should now return a pair t. And then we should probably open pair.c. This thing is fine, but noop is now supposed to return a pair t. So how's it going to do that? Pair t noop. We are not going to create a struct pair p. Rather, we're going to create a pair t p. This thing has to be a pointer, and it has to be a pointer that we can return. We have just learned how to do this. This is our first application of malloc. So I'm going to malloc this. By convention, before I do a malloc, I cast the return to be the type that I want. So I'm going to pair t cast the malloc. I'm going to invoke malloc. How much am I going to malloc? I'm going to malloc size of the struct pair. Following my usual coding convention, I would have called that struct pair struct. I was trying to keep things on one line on the slides. Okay. And I think that's probably good to go. We'll save that. We'll open client.c, I think it's called. There it is. And this is now a pair t. What's the previous word? So if I did DE, it would delete the next word. I don't know how to delete previous. That's the whole line, maybe? I don't know. That's annoying. Oh, I have different indentation settings in different places. Okay. Let's save that and let's make that. Okay. This didn't work, but it caused a complete different set of problems, which is perhaps good. It appears that the problem is called that I have a type named stucked. Did any of you see that? And you didn't say anything? You're such a prankster. You're such a silly goose. Ah, okay. Those are the errors I was looking for, right? It's always reassuring when you see the errors you want to see, right? Previously, when we were working with structures, we used dot notation to look up members of those structures. P, this P, that is a pair underscore T. Pair underscore T is not a structure, it is a pointer to a structure. GCC is asking me if I'm serious about wanting to look up the entries in a pointer, because pointers don't have entries. That doesn't make sense. It is against the law to do this, and so because I'm breaking the law for my crimes, I am sentenced to once again open Vim and attempt to not make a typo in front of my students, right? And so I'm going to do that. I'm going to type vim pair.c. Now, this says p.x. P is a pointer, and if I want to see the value at location P, I use, I'm not in insert mode, I use asterisk, which tells me the location of that. If I had an integer pointer P and I wanted to see the integer, I would say star P. Now, for what I'm going to refer to lovingly as a God-forsaken reason, star binds less tightly than dot, which means this says look up the thing at location p.x. I know, I was surprised too. And I can tell you don't believe me, so I'm going to exit out of Vim, and I'm going to make this, and we're going to see what the error looks like, okay? Oh, look, P is a pointer. It doesn't care about that star over there. Okay, not to worry, I have a plan. I have an ingenious plan. I'm going to use a little thing I like to call parentheses. Okay, previously there was an error at line 9 of pair.c, and I suspect, but I don't know for sure because I was the one typing, so anything could have happened, that that error is going to go away. By golly, would you look at that? There's now only an error at line 10. But you think, why would you have gone through all of that effort when you can just do literally exactly what the compiler tells you to do? Doesn't that also work? Well, let's find out. Previously, there was an error at line 10 in pair.c. Let's see if it has been banished to the shadow realm. And by golly, there's no errors left in. So anyways, those two things are equivalent, and one of them looks nicer than the other. My impression is the object-oriented languages just gave up keeping track of what is and isn't pointers. So for example, I still do not know if an int is a pointer or not in Python. So it doesn't really make sense to ask for it to have arrows sometimes and dots other times. In fact, I'm pretty sure 1 through 100 are numerical values, and everything bigger than that is a pointer, but I'm not completely sure. So let's go through and make some of the other changes in client. Now, I suspect if you're a Vim Power user, there was a way to do that with multi-cursor, and I'll probably learn that sometime in the next 5 years. I think I almost need to, like, did I not save? Okay, what did I do wrong here? Cat. Invalid use of undefined type struct pair. I thought this was going to work. Now I'm sad. I'm not that sad. What's the answer key say? Really? I thought that's what I was doing. Wait, no, okay, no, this makes sense. That was an intended error. I knew that was going to happen, and I did it on purpose to teach us something. I am also very tired. Oh my gosh, it's only 8:40. We have 72 minutes left. I guess I have an entire slide deck left. Okay, maybe that one's fun. It's on blockchain. Okay. Okay, so here's the deal. Which I would like to remind you that I knew the whole time this was the deal. The deal is client doesn't know that there's X's and Y's in there. How would it know that? The X's and Y's are obscured from it. They're in another .c file, and it has not included that .c file. Now I think, here, let's just do an extremely cursed example. I'm pretty sure this is allowed. You should never do this. Yeah. Okay, that's a little sketchy. But we got a different error. So that's kind of cool, right? So let's go ahead and get rid of that line. And then we'll save that. We'll open hair.c. And we'll now write a setter. No, we won't. Oh, okay. All right. So we're going to set. Now, if I were writing in an object-oriented language, the setter would be a method of some object, and the first argument would be self. So I would have something called, for example, set, and then it would have itself. In C, I have to specify what that type is, and the type of self is pair T, I guess, because we're going to call it on pairs. And then I'm going to set the X and Y values. By convention, I think setting operations do not return anything, so I'm going to put a void here. You could also return a Boolean to denote a successful set operation. I think that is the thing that would make the next most sense, right? Do you like returning Booleans?
I like throwing error if it's an invalid value.
You just throw an error.
I like using my 4960 library.
That's what I use for my Booleans too. Yeah. I just, so it's to denote a Boolean return value of true, I just fill the entire hard drive with ones. And then if it's false, I just fill the entire hard drive with zeros. And it's great because I'm never out of storage space. Just like every time I return from a function, it reformats. Yeah, yeah. We know how to have fun in this class. Okay. Int. They're ints, right? Yeah. Okay. Okay. And then here we can do p x equals x, p y equals y. Probably? Yes. Return. Okay. So we set, we have to add set to pair.h. So it was of type void set. Hey, it's very close to September. Summer has come so fast. Something will never last. Okay. I'm frequently confused with Billy Joe Armstrong. Frequently. Okay. Client.c. I hear Billy Joe Armstrong only uses C89 and just has the flags hard set on all of the make files. So, and, you know, just something to think if you're a big Green Day fan. Okay.
Like Google band number listing just had them listed. Okay.
Really?
Yeah.
That's cute.
No,
I like that. Oh, hey, it worked. Oh, hey, it worked. This works. Ta-da! Stuck the landing. Okay. You've already done this. These are opaque pointers. They should have been void stars, right? Or they should have been structs. And now you know everything. I was going to live code recursion if we had extra time, which we don't. I think. Yeah, time to move on. I'll just start live coding random stuff if we get to the end of class anyways. Wait, no, this was the assigned paper for today. I thought I assigned a different one. Okay. Anyways, yeah, read the Bitcoin paper. I'm gonna go refill my water. What are we doing? Background. Okay. Drink break.
It's fair. You want to be on the top and stay here. Absolutely. That's it. That's what makes me laugh. I didn't know that. That is the course. And congratulations.
You actually can't teach blockchain on whiteboards pretty well.
We have to use the whiteboard in the classroom to show the slide number.
Yeah, I noticed that when I walked through. I never know if you like all of you over there are like happy or like you just don't care anymore or like no, I know like you care about being here, right? But like care about like whether there's a whiteboard there. Like it just doesn't feel like it affects you, right? But like it is a little goofy, right? Yeah. You're just like you're really into that activate Windows thing. I think it's cool. It's like my computer has a tattoo, right?
Like second smaller activate windows at the top left.
So what I really want it to do,
Yeah.
I want it to bounce. Yeah, I think the bouncing would be sick, right? Like if I could get it to do that. Um, also, I don't perceive it, so like yeah, I don't even know it's there. Yeah. I think once you get inoculated against the inactivate windows, you just never have to pay for Windows again. And apparently you can turn it off in the registry, and I've just never even bothered doing that. So, anyways, kind of the fact that you bring it up makes me think I should leave it there, you know? Okay. You can't let the haters get you down. Okay. Speaking of getting down, if you're a player hater, don't player hate on me. Yeah. Anyways, yeah. I'm using Windows, right? Like that should count for something, right? Remember that entire lecture I gave on how you can actually do development on Windows? It's true. You can, I think. No one's ever done it. Okay. Oh, this is right. Okay, so I made these slides several weeks ago when it had been like a tasteful amount of time since the last global financial crisis, right? And then I started learning a ton of graph theory and didn't really remember what slides I'd made. And then I walked into class today and was like, oh. So, anyways, we're going to talk about a financial crisis. So, the first financial crisis, and it's funny that these things happen roughly once a decade, maybe a little bit more often. Kind of love that. Anyways, in the year 2000 or around about then, and I don't remember this one that big, and it wasn't that big of a deal. Sort of Silicon Valley was taking off for the very first time, right? And when I say Silicon Valley is taking off, what does that mean to me historically? In the United States, historically, all of the sort of concentrated wealth, so banks, industry, all that stuff has usually been based in and around New York City. And so decisions about things about sectors of the economy tend to be made in New York City. I think of the United States as having like roughly 20% of its economic activity being the energy and transit sectors. And why do we combine both of them? Well, they're both petroleum based, right? Maybe another 20% for healthcare, probably not quite 20%, maybe 15% for education, right? Few other things. I think there used to be a US manufacturing sector, according to some people, but I don't think there's been one like in my lifetime. But also, like, even with a relatively small manufacturing center, like millions of cars are made in the United States, right? It's actually very, very difficult to make a car. Very few countries can make a car. And of the major industrialized economies in the world, one of the foremost ones is Germany, and their largest companies produce cars. They are predominantly an automobile company or country, which is not necessarily true of other countries. But I think when Japan was industrializing, Honda, Toyota, and I believe to a lesser degree Nissan and Mitsubishi were like very important parts of their industrialization, even though they're predominantly now a Sony economy, I think. Um, this has been less true with more recent industrializing nations, which are almost overwhelmingly tech economies. I think very highly of the economic developments that I have seen in the Republic of Korea or South Korea, in Taiwan, which is not either a nation state or not a nation state, and also Vietnam. Um, Korea overwhelmingly industrialized on the basis of Samsung, which makes smartphones and solid state drives, and like not that much else, right? Like they kind of make a little bit of everything, but like mostly they make phones. And they're competing head to head with Apple, which is a $1 trillion US company, and they seem to be doing just fine. Um, and then Taiwan has the Taiwanese Semiconductor Manufacturing Company, which is the most important company in the world, and somehow not valued at $1 trillion. So someone's going to figure out how important they are at some point. Um, and then Vietnam has a relatively diversified economy, but they seem to mostly be focusing on technology products to me. They make a lot of chips and printers and things like that there. And that's also true of like Thailand and Cambodia, right? So many of the countries that are sort of currently becoming industrialized are doing a tech focus. We're sort of seeing that same trend, in my view, in the United States at about the same pace. In 2000, neither Sony nor Samsung was holding up an entire national economy by themselves. Taiwanese Semiconductor Manufacturing Corporation was just sort of getting started, though it was probably already the most important company in Taiwan. I think our tech sector in this country around that time was in the 1 to 5% size, which was huge and like earth shatteringly huge at that time. I remember there being conversations about like, oh, is it an information economy instead of a manufacturing economy? All this stuff was happening. People had no idea where we were going with data centers, right? Um, when 1 to 5% of the economy goes through like a massive financial crisis, that is a big deal. I think we all remember the collapse of the Silicon Valley Bank, which was a contained minor collapse isolated to Silicon Valley. It was bailed out instantly, still massively disruptive, right? I think of the dot-com boom as being very similar to that. My understanding of the dot-com boom, and I'm not an expert on this, is that tech companies were coming out, their valuations were getting pushed too high based on expectations of how fast basically e-commerce and the internet economy could grow. And these expectations were unrealistic. One of the things I think about back at that time is I do remember being alive around 2000, and I remember people were scared to give their credit card number over the phone or to type it into a computer. And if most of your Americans, and only Americans are going to be buying this stuff in this year, right, are unwilling to put their credit card number into a website, you fundamentally can't make money on the internet, right? So these technologies were not yet mature. Their valuations were probably too high, especially if you're looking at quarterly profits, which just weren't going to be there for decades. And so there was a bunch of public IPOs. They went out. The companies got too valued. Everyone got skittish. And then this dot-com sort of bubble burst. The valuations of all the companies tanked. Many of the companies went under. And blah, blah, blah. Takeaways from this are there were two main takeaways. On the technology side, technologists, so people that just cared about like maybe the science of how computer science worked or something like that, they noticed that many of these companies and many of the legacies they left, it seemed like the core problem was that there were expensive central servers that were responsible for maintaining services. So when you have some service on the internet, it has some corresponding server. That means if that company goes out of business, any of the data that's stored on the server, any of the promises that were made by that company also go away. And this was a big deal because of various things going on, but people didn't want to put their credit card number on the internet. So they also looked up other things like internet banks, and you all read the Hashcash paper, right? So people were trying to invent other ways to spend money on the internet. But all of these other ways relied on a company with a server not going out of business. And that was sketchy. You sort of don't want a Silicon Valley fly-by-night company to be responsible for holding on to your money, right? So that was the first sort of common trend. Everything was getting centralized and it had single points of failure. The other thing that happened that was kind of interesting is the valuations of all these companies dropped by up to 80%, and housing prices did not go down in Silicon Valley. And that brings us forward to 2008 with the global financial crisis. This thing has, I think, also been called the GFC. I see it called the GFC more than the Great Recession. I am not a macroeconomist, and I have no desire to be, but my understanding is the Great Recession does seem to be worse than most recessions and not nearly as bad as most depressions. So it is kind of this intermediate thing. It is also my impression. I'm not a macroeconomist. It does seem like wages are still deflated from 2008. So I think wages were increasing at a fixed rate and then they like sort of didn't increase for a while. And now they're sort of back to increasing at the same rate, but there's like years of lost productivity that have never seemed to have been made up. And that's anomalous compared to other recessions in my view. So I think like whatever happened with like stagflation or something under Reagan or something, that stuff all canceled out with law of large numbers by the 90s. So I think the Great Recession is a little bit anomalous for that reason. And I think the reason it's anomalous is because of its scale. The dot-com boom took out a lot of the tech sector when it was 1 to 5% of the US economy. 100% of the US economy is run through Wall Street, regardless of sector. So when there's a crash in Wall Street, it takes down everything. And in fact, when the US collapsed, it was called the global financial crisis because it basically took the EU with it. My impression is that East Asia got hit pretty hard, but maybe not as hard as Europe. And this was generally not good. Now, if you're purely thinking about network science or systems engineering and you're looking at this, and perhaps you're a technologist, you think, well, I thought in 2000 with the dot-com boom, we realized you couldn't centralize money. And then it looked like in 2008, the collapse was caused by the centralization of money of a centralized currency that was backing Wall Street. And so the Wall Street bailouts were caused by the presence of a central bank, according to some people. I don't know that I've necessarily been persuaded of this, but I was much more persuaded of this in the case of the Greek financial crisis, where they were unable to float their currency. It tanked the Greek economy. I think the Germans had to bail them out, but it's like sort of unsurprising the Germans are bailing you out because they're like the third largest economy in the world, and they've also monopolized all the economic development in Europe. So like maybe if you're in Europe and you're out of money, Germany should just give it to you, right? And actually we kind of do that in the United States, where in the United States, if you run out of money, either California or New York is going to cut you a check. That's just like where the money is, right? So anyways, one of the takeaways from 2008 is that centralized banks are a liability, or they're politically weak, or they're difficult to defend, or people don't like them or something. There have been a few things that look a lot like currency crises since then. After the Russian land invasion of Ukraine, the United States did a bunch of things with the global financial sector to induce a, I think, comparatively short-lived currency crisis on the Russian ruble, right? So this can be used as sort of an act of war or something like that, right? So currency crises have been around, but Greece, 2008, and more recently Russia are the ones I'm the most familiar with. At any given time, there's some developing country that's going through something that is either a currency crisis or an actual economic crisis, and usually it's hard to tell immediately. So I'm thinking of Argentina there. Okay, so we imagine again that we are technologists, that we care a lot about what happened in the dot-com crash in 2000. We care a lot about what happened to the global financial crisis in 2008. And perhaps we are true believers in technology, and we believe that the problems we're seeing can be solved with a purely technological solution. This is perhaps not an unreasonable thing to believe. You could argue that fiat currency is a technology and solved a lot of problems, and I think that's a reasonable thing to believe, right? But if we are trying to put together some currency that is not vulnerable to a global financial crisis, and that is going to solve the problems that were supposed to be solved by Netcash and Hatcash and the other dot-com era technologies, we would probably want it to have a few attributes. And the attributes I'm thinking of are, if I am the client, if I'm someone that uses, if I interact with the APIs of this currency system, I would like it to be non-physical. I don't want to carry it around in my pocket. I want it to be non-governmental. If I transmit myself from the United States to Paris, I don't want the value of my currency to change when I cross international borders, right? This is very important on the internet because bits are crossing international borders all the time, right? When you go to a website, you don't know if the prices are in whatever, I guess they use euros in Paris, dollars in the United States. And I think, are the Canadian dollars also called dollars? So there's $2 just in North America? Good for them. I hear the Canadians have a strategic maple syrup reserve. That's the connection. Canada's like right there. Like, there's a train station you can go to Canada in like 4 hours.
Canadian games.
Great Canadian.
It doesn't have a French sheen as well.
I would be so disappointed if it doesn't. Okay, so I got no flavor this time. That's like some pretty tasty water. That stuff slaps. I'm not sure about Orange Oasis anymore. Maybe I hate seasons. Okay. Okay. There's another feature that physical money has that maybe we don't think about, which is that there's only one of it. I know, at least when I was a small child, the first time you see a photocopier, you're like, I am definitely going to photocopy money, right? And I guess that doesn't work very well. I never tried because I heard it was a felony, right? Whatever. I think felonies are like cool now, right? Like, who hasn't committed a felony, right? Um, but essentially, what you want to have is you don't want to have this like sort of trust problem where if someone spends some money, you can't tell if it was real or you can't tell it was their money or you can't tell if it is money or anything like that. And so we call this non-reputable or the property of having non-repudiation. So if some money is spent, you know it was real money, you can have some confidence in the system, right? Transactions cannot be denied to have happened is sort of the network theory definition of this, that it after something has happened, you can't go back in time and change the record. Oh, the record, like a record data type? No, well, okay, all right, okay. Okay, so someone, and this person was, or a group of people, probably a small group of people, was using the name Satoshi Nakamoto, I think, which is the author of the Bitcoin paper. Where is it? I'm clicking. Wait, did I turn the recording back on? Oh, thank goodness. Okay. BTC08. Here it is. Satoshi Nakamoto. I don't know what gmx.com is. Cool. German?
Yeah.
Does Satoshi Nakamoto? All right, whatever. Okay. There is like an actual existing person named Satoshi Nakamoto who seems to have no relation. Like occasionally some like journalist calls up this person and it's like, I'm not really like a cryptographer. Like, cool. Okay. So Bitcoin comes out. Bitcoin was designed by someone that knows roughly the same cryptography stuff as you do, but has probably thought a little bit more about it and maybe is a little more skeptical of governments. And you would think companies, but it doesn't seem skeptical of companies to me. Bitcoin is developed to have no centralized server. Doing things without servers was pretty unusual and considered pretty hard in 2008. I don't know if there was stuff like LimeWire and Napster and like sort of all of the sort of music piracy stuff was probably the closest anyone had seen. And I don't think anyone had the impression that they wanted to be storing their money on Napster. So actually doing something rigorously and confidently and trustworthily without a central server was like not considered something that could be done, right? Generally speaking, if something happened on the internet, the way you would have confidence in its trustworthiness was that you would trust whoever was running the server, and then somehow you would have some chain of trust believing that you were actually talking to the server you think you're talking to. And that is why this thing is on HTTPS instead of HTTP, right? So you can be confident that Professor Calvin certified these slides as completely authentic. You can trust me. So the earlier failed digital currencies failed because they had a central server. And the network theorist people thought of the US Treasury as being something an awful lot like a central server. In fact, it does serve currency, right? Just not over the internet. Well, now it does over the internet, right? But I think in the olden days, they just carried like hay bales of, I think it's called like filthy, dirty cash money, right? And you just like threw them at Bear Stearns.
That was the bag. Like,
yeah, with the dollar sign on side. Yeah. And you like wear like the little like mask thing, like Zorro. Yeah, I don't know. And so it's actually very easy to solve the problem of not having a central server. In fact, I personally don't have a central server. I already solved that problem. It's very easy to not have things. But unfortunately, Bitcoin had one additional constraint, which is that you had to be able to perform transactions. And I was like, ooh, that's hard, right? Because I am not able to perform transactions. I'm not even sure what a transaction is. But every once in a while, I walk into like a little coffee shop and I'm like, may I have one hot oat milk, small mocha to go? And they're like, why do you have to talk on your hands? I was like, why do I need 5 modifiers to order a mocha that won't make me sick, right? And when I do that, then most of the time you have to pay. But if you're like funny enough, sometimes they forget, right? Usually what happens is then they're like, that'll be like 8.25 because of the economy. And I'm like, ugh, right. And so I like whip out someone else's credit card that I borrowed and I tap the little thing. And that's a transaction, the exchange of goods and services. So we want to be able to move Bitcoins to someone else in exchange for giving them giving us a small hot oat milk mocha to go, right? How do we do that? Well, in real life, this stuff is all backed by like the laws of physics or whatever, where like when you physically give someone a dollar, you can't still have that dollar obnoxious, right? Very difficult to do this with numbers because everything in a computer is just a number. And if I haven't convinced you of that yet, I'm not going to do it, right? So somehow there's just some numbers somewhere. And maybe you're like, ooh, what about the numbers that are on the central server? We also got rid of the central server, right? So like all of my filthy dirty cash money lives on a server owned by Wells Fargo because like which bank are you going to pick, right? So anyways, I picked that one. And so like their central server is authoritative and I'm just sort of like hoping that they like either don't collapse or get bailed out if they do or something, right? And it doesn't keep me up at night. I don't worry about it all the time or anything, so I don't want to give you that impression. But instead of doing that, maybe what you can have is you can just like everyone in the universe, or at least everyone in the Bitcoin network, can just agree on who has how many dollars. Has it been shaking all night? Is that uncommonly shaky?
It's part of not.
Oh, it's that thing. Oh, it's because I didn't activate Windows. Okay. But see, these windows appear activated. Okay. Okay, so we're like, all right, we're just gonna have everyone agree on who has what money, right? We're not gonna trust central server, just everyone's gonna agree. And when everyone agrees on who has what money, then all we have to do is everyone has to agree on every single transaction. You're like, wow, like I've never agreed about anything with anyone, right? So this sounds hard, right? And you're just not allowed to spend coins you don't have, right? So everyone will look and they'll say, oh, your current account balance is 0, so it would be difficult for you to buy that small hot oat milk mocha to go. And be like, I want it. And then maybe they'll still give you one, right? And how is it going to do this? Well, we're going to use cryptography. We're going to use cryptography instead of servers. Now, there's still servers in the mix here. There's just not one server. So there's cryptography happening on servers, but you don't care which server. And that's sort of the benefit here. There's no central authoritative server. We're going to use RSA for people to be able to say who they are when they're trying to spend money. And then we're going to use SHA to make sure that we all agree on what happened. We agree that the money was spent. So only a certain person can start the process of spending the money, and then once it happens, no one can change it. We're going to do that with SHA and RSA. This is based on proof of work, and we will get to proof of work in a bit. I'm going to follow this paper quite closely. You should read it. In this class, I think I'm requiring you to read it, but I'm going to go over it anyways. This is the Bitcoin Genesis block. This is the first block. This is, or perhaps the 0th block, or perhaps the -1th block. You had to start with something. So imagine, if you will, I'm saying, I have all of this digital currency. This digital currency is defined not by someone having a coin or a token, but is defined by someone having had a transaction to them, which gives them that currency, right? Well, then the currency has to start somewhere. I think I'm accustomed to thinking of US dollars as being printed somewhere or also minted. So I'm from Denver, Colorado, and there's a building called the US Mint. And you go in there and they're like stamping quarters onto blanks or something. I don't know how money works. Um, and I think there's like only two places in the US that do this. And like if the quarter got stamped into a blank at the US Mint in Denver, it's just real, right? It's just worth 25 cents. Everyone will accept it's worth 25 cents. Um, the US dollar, I think, is backed by a variety of things. So I think I wonder if I have a dollar. Probably not. I think they say like valid for legal tender in the United States. So it's backed by the law, and the law is backed by the police. And like for a while, it was tied to the price of petroleum, which is backed by the United States Department of Defense, right? Um, I purchased some gas today, right? And I was able to do that with US dollars. And like, I bet it's really, really hard to buy a physical good with Bitcoin. Like, I think it's possible, and it's like probably a very painful process, right? And so, if you don't have these sort of quarters or dollar bills or credit cards floating around, you have to do something else. And so the way they sort of bootstrapped Bitcoin was they made a Genesis block that said Satoshi Nakamoto had all of it or something. And then Satoshi Nakamoto gave it to some other cryptographers. And that's sort of how they started the system. So anyways, this is what a Bitcoin block looks like. This is a hex dump. So these are offsets. These are bytes, and these are ASCII values. And I'm just going to point this out to you. I think it's important to not overly disentangle Bitcoin from the political situation that it came into existence in. But if we look at this, embedded in the first Bitcoin Genesis block, which has the benefit of telling you the, I guess, like, what is it, the earliest possible date it could have made, because it has to have been made after this headline comes out. And everyone in the world can see this headline. This is a headline from the Times of London. It says, Chancellor on brink of second bailout for banks, which I guess was offensive to some people. I remember in 2008 when I still knew what was going on politically, I didn't want the banks to be bailed out. And I guess I was probably just as correct as I am now. But now I don't remember why you care if the banks are bailed out or not. Does anyone know anything about banks? How about Banksy? How about Tyra Banks? How about the banks of the Willamette River? I think that's all I got. You can have like banked turns in NASCAR? A banked shot in basketball? Yeah, see, okay, so we know what banks are, right? Okay. We probably also know what blocks are. This is more or less the first paragraph of the Bitcoin paper. But I'm just going to tease out a few things. Bitcoin was really, really preoccupied with this notion of double spending. That if someone has a piece of paper that says, I have 1 Bitcoin, that they show it to 2 people. And they give those 2 people the same Bitcoin. Money is sort of only useful if it's finite, because there's a finite amount of stuff, and we use money to distribute the stuff. So if someone has infinite money, it loses its usefulness. Fair enough, right? So we're fascinated with this double spending. Here are the features Bitcoin targeted. Peer-to-peer, which I think of as no central server. Distributed, which I think of as no central server. It is time-stamped. That's going to be a problem for us. And we're just going to hand wave it in this class. I could teach an entire class on time. And in fact, when I first learned about Bitcoin, it was the last paper we read in a class called Advanced Networks. And everything we talked about prior to Bitcoin was about how hard it is to achieve distributed consensus and how hard it is to figure out what time it is. And then we said, good thing we don't care any of that. Here's Bitcoin. And so I've never really been that convinced by Bitcoin for that reason, because I sort of spent a semester learning why it wouldn't work. But it turns out it is very difficult to figure out what times thing happened down to the nanoseconds. And Bitcoin blocks come out every 10 minutes. There's a very, very large number of nanoseconds in 10 minutes. And it's usually possible to figure out if something happened in the last 10 minutes or not. Right? This word says computational proofs. That is proof that some computation occurred. That is not a proof in the sense of a mathematical proof. We did the counting necklaces proof. That is a mathematical proof. That's a different type of thing. That's a proof that some statement about mathematics is true. This thing is a proof that some computation occurred. Why is it important that computation occurred? Because we have to prove that something happened in the past, right? So something must have happened. There's going to be a chronological ordering of events, which again is non-trivial, and we're going to be able to keep track of transactions. If you look at these things, you're saying, we're going to put the transactions in chronological order, and then we're going to prove it. And so that's the direction that. And how are we going to do that? We're going to do it with a timestamp distributed peer-to-peer network. Not too bad. The coin in Bitcoin, it is not a physical coin, it is all digital, and it is represented as a chain of ownership. Satoshi Nakamoto had some coin, Satoshi Nakamoto gives it to someone else. That person exchanges it to someone else in exchange for some goods and services, and that exchanges it to someone else for goods and services. But the coin is the chain of ownership. The coin is currently owned by the most recent owner, and at any given time you may spend the coin by you as the current owner, sign a certificate that signs it over to someone else. In this sense, I think it is very similar to like the there's like things related to cars that are either called pink slips or blue slips. Title, yes. And for example, the title of this slide is transactions, right? So we know what titles are. Okay. So an astute observer will notice that unless you finish the list T assignment, you don't actually know a way to store an arbitrary number of owners. Which means, I've tricked all of you. Teaching a class on Bitcoin and cryptocurrency was actually just a motivation to teach you about linked lists, my favorite data structure. Yes! Gotcha. You've been bamboozled. So anyways, a Bitcoin is a linked list. And everyone loves linked lists. And I know what you're thinking. You're thinking, can't I just implement it as an array list and no one can tell? Yes, you can. Yeah. So these records, because the record is not the printed coin from a mint, they can be stored in many places. So this allows us to have our decentralization. Why is it useful to have decentralization? Imagine I'm Satoshi Nakamoto and I am operating the first Bitcoin node. And perhaps I realize that my sick gaming rig I've been using to mine Bitcoin, I can instead use to play Crisis, because it's 2008, right? And Crisis just came out. You need like a really powerful GPU to play Crisis, right? So you're like, hey, I got to take down my Bitcoin node for a while so I can play Crisis. Then all the other cryptographers that don't have good hand-eye coordination have just been playing Minesweeper. They can keep playing Minesweeper and they can operate their Bitcoin nodes, right? So you can take your servers and nodes online and offline anytime you want. All you need for continuity is even they can all shut down for a while and then just wake up 2 years later. That doesn't really offend anyone. That would be weird, right? But as long as the records are maintained somewhere. And you can verify the authenticity of the records. So the records can be produced by anyone, but the coins cannot. The coins can only be produced by either Satoshi Nakamoto giving you one. And I sort of paper over this because I don't care about it that much, but this is what drives the Bitcoin mining thing is you get a little bit of coin every time you successfully mine a coin. And we'll define what mining a coin is like. Or mining a block. The records describe ownership and coins cannot. So every once in a while, someone like drops a quarter and there's no way to know who dropped that quarter. Bitcoins do not have that problem because if I drop something that says Calvin Deutschbein owns a Bitcoin on it and someone else find it, they'll be like, oh, I guess Calvin Deutschbein owns a Bitcoin. So I can still walk into that cafe and say, trust me, I have one Bitcoin. I don't have my wallet with me, but you can check that I have the money, that I'm good for it by just looking at the decentralized blockchain. And then usually you get asked to leave the establishment, but it is true, right? You can say that, it's true. You all know Professor Heather Kadada Smalley. So she brought her daughter Hadley into the office one day for some reason. And apparently when she went home, she kept saying the words decentralized cryptocurrency on the blockchain. And they figured out it was me. Like, I was like, I should have taught her something else, right? And so then the next time I was like, I should be more subtle. And apparently she's been asking Heather what lambda calculus is. So I think I'm not allowed to interact with children anymore. I have a little book called Bitcoin for Babies, and it doesn't make any sense. So I was like, I should write the good version of the Bitcoin book for babies, right? Okay. Here's a transaction. I have a coin. I sign the title over. That's it. Satoshi Nakamoto was very invested in the idea of multi-transactions, where multiple people pool their resources together to give their coins to multiple other people. It was non-obvious to me when I first read the paper, geez, in like 2013 or something, like a long time ago, why you would care so much about that. My impression is now what happens is every single transaction someone makes a new digital identity. So there's no way to link any of your digital identities. What that means is if you get paid 3 times and you need to spend more than those 3 values, you create a transaction that has 3 spenders. And you don't have to do spending between them, right? So once you finally pull all the resources together, someone can then conclude, those 3 transactions were all the same person. But until you have to spend all of the money at the same time, no one can tell. So that's pretty cool. So anyways, there's that sort of lengthy digression in the paper about how, you and your N friends collectively own M coins. They can transfer those M coins collectively to P other new people. And I was like, why does this matter? Why does this matter? Why does this matter? But it kind of makes sense. You could equivalently argue, even if you can only do 1-to-1, couldn't you just, if you're trying to pay someone, be like, hey, I need you to make 4 new digital identities, and I'm going to give a quarter coin each to all 4 of them from my made-up digital identities, right? That seems fine. But I think that leads to atomization really quickly, and that can probably be pretty annoying for record keeping. So some number of people give some number of coins to some number of other people, and we write this down. And you have to write down how many coins go to and from each person, right? Because you have to have a chain of ownership. You are allowed to cut up the coins and slice and dice them. I think a coin is a very big unit. It's worth like some unbelievable amount of money. How much is a Bitcoin worth? Do we think 8K? Wow, so if I had one of these, I could take a year off. That's crazy. And then I think people usually refer to the maximally divisible unit as a Satoshi after Satoshi Nakamoto. And it's worth like nothing, right? So you can divide things up into this amount. And I'm just going to trust bitbo tools.bitbo.io/Satoshi US dollar. This seems like a trustworthy website that I can trust. Alrighty. I do love the internet. It's so funny. Okay. Okay. How am I going to sign this, right? I can't just sign my name on a PDF on the internet because PDFs are owned by Adobe. Everyone hates them, right? So we need another way to sign this. And we need something that's not owned by anything. And you know what no one owns is the RSA public key cryptographic system because it's public. It's right there in the name. It's a public crypto system. I guess that's like the single equals assignment, like where do the words go? It is a publicly owned key crypto system, right? That's not true. I made that up. Don't listen to that. Okay. So here's the process, and I found this like ludicrously hard to explain, and maybe it'll make perfect sense to you, but it took me forever to understand digital signatures for some reason. And now when I look at these slides, I can't even figure out what I got stuck on. So I don't know how hard this is. Here's the deal. You write down the transaction. Okay? Write it down. It says, Professor Calvin gives Calvin Deutschbein $N. And then you compute the SHA hash of that transaction. Step 1. It's really getting me. Then you RSA encrypt it, but you don't encrypt it with your public key. You encrypt it with your private key. We usually think of that as decryption. So in a way, you're thinking of the transaction as a ciphertext. Okay. Then you release 2 things. You release the hash of the transaction, and you release the ciphertext of the transaction. How does someone verify its authenticity? Well, they take your public key, because you already used your private key, and they decrypt with your public key. We didn't talk about this that much, but it doesn't matter if you use the private key or the public key first, right? The only thing that matters is you have to raise something to a sufficiently high power, and then it loops around and you get the original value back, right? So when you get the original value back, that's when you get the ciphertext back. Easy, right? So I release the hash and I release the ciphertext. Someone goes in, they decrypt the ciphertext with my key, and it says, someone pays someone some amount. And they compute the hash of that, and if that hash matches the thing I released, then only I, the person that holds the private key, could have possibly created that message. Because it's exactly as secure as public key cryptography is, right? So that's how it works. Here's a diagram. I thought a diagram might be slightly easier. I don't know if it is or not. Here it is zoomed in, and we'll talk through this. Okay, so I'm attempting to use the Bitcoin network. I'm going to say I am going to give n coins to someone else. We call that the unencrypted transaction. Okay? There's an arrow going over here. Where's that going to? It's going to SHA-256 down off the screen. But the first thing we do is we're going to encrypt it. How are we going to encrypt it? Well, we're going to treat the encrypted transaction as a message. Remember, we use the notion of messages in RSA, and so that's what we're going to use here. Now, for the private key, we're going to use that in the encryption stage. This is a difference, right? And we're going to create a ciphertext where we're using the E value as the D value. So we're going to use the decryptor as the encryptor. Totally fine, totally above board. This is going to give us an encrypted transaction, okay? Now, we can release that into the world along with our public key and say, this is my public key, right? We can decrypt it, or someone else can decrypt it more properly because we want someone else to trust us. So anyone on the Bitcoin network can take the ciphertext, can take my public key, and can get the plain text message back, right? We call that the decrypted transaction. Then what do we do? Both the original one, the unencrypted transaction, and the second one, the decrypted transaction, both of those we pass through compression. We compute an SHA-256 checksum, and we compare the checksums, and we do an integrity check. Why do we do this? Well, this unencrypted transaction is never released, right? So no one can actually see that. They can only see this. The public gets this thing, a hash digest because it's smaller, it's just what we call it, and they get the encrypted transaction. So there's a public-private split right through here. But at the end, the public can decrypt, checksum, compare if the two hashes are the same, which is a very small number of bits to compare, right? It's only 256 bits. It's very simpler. And if the two hashes are the same, then you accept the transaction. Easy peasy. Does that make sense? Does anyone want to ask me any questions about that?
Go ahead. I was just saying, you said that you don't understand the message. That's not the same.
It is the same. It is the same information, but no one knows that it's the same information until they compare the hashes. So this is the only thing I release. People can determine what the transaction is from that, but they don't know if they've determined it correctly. They don't know if I'm really who I say I am unless the hashes agree, because otherwise it is easy to create something, well, it is comparatively easy to create something that might decrypt to a possible transaction. But it is very difficult to create something that can be decrypted to a possible transaction and also has some corresponding matching hash. Yes. Yes.
So my question was, for a transaction to be approved or accepted, someone has to go through this process and give a stamp of approval and go, check that, right? It doesn't count.
Yeah. Someone in the sense of like a script running on a server somewhere checks.
Okay.
Mhm. Mhm.
Does that script have to belong to your automated running?
Yeah, totally automated. So I think the way this works is there's a Bitcoin tier 1 network, which is harder to get into. So that's the power users. And there's a tier 2 network for smaller transactions. But the tier 1 network is when a big transaction comes through. So we're talking about moving tens of thousands of dollars, right? That's broadcast to everyone in the network. And everyone in the network is some number of usually mining consortiums, right? So collections of Bitcoin miners. When they see that transaction, they get a hash value and a ciphertext. And a public key because they know it's affiliated with someone. So They say, okay, you have your identity is that public key. Your public key is your identifying information. I'm going to decrypt this message with your public key, and then I'm going to hash it and see if the hashes are the same. And if it's true, it's considered a valid transaction, and it becomes a candidate to go into the next block. So there's just a growing stack. Oh, it's going down. Sorry, no, the stacks go down. Right. So there's a growing stack of transactions, right? And they're validated. Now, there's one other validation step that we've papered over so far, which is not only do I have to verify it's who I say I am, but each one of those servers is also going to verify that I have enough Bitcoins to process that transaction. And the way it does that is it sees my public key and it makes sure someone transferred Bitcoins to that public key of the amount greater than what I'm spending, greater than or equal.
Do the two people, listen, the two people in the transaction receive a notification when something else has approved of it, or you just kind of like, I hope it got approved.
It'll show up at some point in the future in the public ledger, and we're not that far yet. Oh, my foot's cramping. Okay, sorry. The transaction contains the public keys of the people sending and receiving Bitcoins and the amount of Bitcoins from each and to each person. So when we say like a person has Bitcoins, we really mean the owner of a public key has Bitcoins. Yes, yeah. So the way you demonstrate you own a public key is with a digital signature. You create a message no one else could create. That's a great question, right? Yeah. Yeah. So I suspect millions of dollars in Bitcoin are lost due to like public keys being stored on a hard drive that dies or something, right? Um, to my knowledge, the unironic best practice right now is you think of a meaningful phrase to you, SHA-256 hash it, and use that hash as the seeds of a keygen algorithm. And so you have a way to reliably regenerate your private keys. And then what I've heard is to make sure you remember this, you're supposed to stamp it into metal washers, put the metal washers on a screw, screw it together, and carry it on your person at all times, and hope no one knows that you're a huge nerd that's into cryptocurrency and just takes it off of your body. But anyways, I guess some crypto power user got really into this like stamped on metal thing because like their house burned down, but they'd like stamped their private key onto metal. And so they were able to retrieve their Bitcoins, right? So great thing I would recommend doing is like not staring too long directly into the sun about the Bitcoin stuff because it is like completely inane all the way down, right? But I don't know. I think it makes sense if I'm like, hey, I have a 4096-bit integer, but if you can remember it for the rest of your life, you can have $1 million. You'll figure something out, right? And people are figuring out increasingly good things. I think if I were to do this, I would not use the stamp on metal technique. I think I would probably store it on 2 hard drives that I keep at different locations. And I would make sure that they're alive pretty regularly. And if one of them failed, I'd just replace it. But like even 2 seems fine. Like the likelihood of 2 Bitcoin or 2 hard drives failing at the same time is like, I'll bet $1 million that's not going to happen. Right? Oh, absolutely. Yeah. I think that's actually just a good use of your time, right? So like if someone accidentally threw away $1 million in like $1 bills, right? We would be like, that is one of the stupidest things I've ever heard in my life, right? And it is exactly that stupid when you throw away a hard drive worth $1 million, right? Like, I don't know. How many Bitcoins you have?
It was,
Yeah, you can definitely buy it. Yeah, I don't know how much. Let's see. Dump sneer me for sale. Okay, hear me out, right? So say you have enough money to buy a dump. You probably don't need the bitcoins, right? Like you're probably okay, right? Maybe your taxes should be higher, right? Mhm. Yeah, you can write it off on your taxes. Yeah. Um, I think the top marginal tax rate could be higher. Is my takeaway from a lot of the things I've heard about Bitcoin. It's like, how much money do you have? You lost how much money? Um, I think this often.
That's
Yeah, that's like a completely different amount of money than 80 million.
Yes.
Yeah, that's like not only are you set for life, you're very set. Yeah. Well, if you like him, right? Because what if you're beefing with your bloodline, right? People don't think about that enough. They're like, I need enough money for my bloodline. It's like, are you sure you're gonna like all of them, right? Like I have some family members, right, and I love them all, right? But I'm not sure they all need $80 billion, right? Okay. Um, so some of you, I think, were skeptical. What time is it? Oh, we're like high key not gonna finish this unless I speed up. Does it matter? Where are we? Oh, I can definitely finish. Do you want me to go fast or do you want me to stay in depth? Okay. You want just as a bit. When I go, I do watch myself on 2x. I mean, I think I've said this before. There's not like a lot of YouTubers I'm a huge fan of, so I don't know how competitive the discipline is, but I am my favorite YouTuber. So whenever I say I do it for my fans, I'm specifically referring to myself. Okay, here's a quick example. I implemented big RSA. You know, you've seen it. You have ref RSA. I run make. What does make do? Does two GCC operations, big RSA and big key. I run big key. We all know what big key does. It generates an unsafe.pub and an unsafe.bad. I really don't want you to use these things. You see that in the naming scheme. Like, please, I just had to write an email to one of our guest speakers and I was like, I taught them how to write RSA and I told them they're not allowed to use it. And they're like, should you have taught them about? And I said, okay. So I generate big key, and there's an unsafe.pub and unsafe.bad that are going to be read by whatever. I echo CD, pays, PC, and buccarinos. That's compact disk and personal computer, right? And I store that as m.txt message. I big RSA, and what do? That is a D. That's the decrypt. Why? Because this D flag in my big RSA, that encrypts using the private key. And I want to encrypt this message with my private key, not my public key, because I want to create a ciphertext which no one else may create. We take the cat of it. This will be unprintable. Oh, I didn't lie. These are bits. You can hex dump it if you want to. I was out of space. It's much more readable as a hex dump, right? But this is going to be about 496 bits, I would assume, which is odd because it's quite short, but I don't know. Okay, then what do? So I take the ciphertext and I big RSA E it. This is going to take the public key. And I E it into n.txt and I get it back. I get CD, pays, NC, PC, and buccarinos. Do you all say buccarinos for dollar?
I do know.
Like 20 years ago? Yeah. I think I'm showing my age here. I am, in fact, over 20 years old. Um, it just so happened I'd already compiled Shank, so I was able to just use it. So you can shank m.txt and n.txt. I thought it was important to still show the hash here because this thing could have like a bunch of hidden characters and non-printing characters or trailing zeros or something. But if I'm telling my mates that I gave them some money, I just release this thing and I release that thing, and then anyone can do this and then that and verify it was me. As pets, as they say. What stops me from paying myself infinity buccarinos? someone's going to check how many buccarinos I have before I get to spend even a single one. Right? They're going to say, "Do you have at least one single buccarino?" And I'll be like, "Yes, I do. I got one buccarino from Satoshi Nakamoto for teaching this class." If you are getting paid, you have no way to verify that it's not a double spend. Only the network can verify it's not a double spend. One of the thoughts is, oh, we'll just make N coins, but we don't like banks, right? The Bitcoin solution to all of this is something called a public ledger. I've mentioned this a few times. Every single transaction ever is recorded, always. Does that sound like a privacy violation to you? It's a metadata violation, but no one can connect any transaction to you, right? I encourage people, like, I'm not a huge fan of Bitcoin, right? But I'm always surprised by how shocked of this, how shocking this seems to people, because, like, I've seen someone driving a BMW around and I know how much money they have, right? So, like, there are public ledgers of transaction history already. Like, you can look up who donates to political candidates and you can be like, probably if that person spent that much money last year, they have more money than me, right? So many transactions are already public. The entire Bitcoin is 600 gigabytes, which does not fit on this device, but fits on other devices. Exactly 5/6 of it would fit on this device, or one Boolean. So I can store two things. But you only actually need to know the most recent transaction, right? Because that's who currently holds things. And so if you're just trying to prove transactions, you only have to hold on to a 5 gigabyte working set. Now, I would have really, really low confidence in that 5 gigabyte working set if I didn't think anyone had the full 600. But if I thought a few people had the full 600 and they were checking every once in a while, that'd probably be enough for me. I'm not too worried about that, right? You can generate as many keys as you need, basically. That's how it remains quasi-anonymous, right? This link broke because it's a link to a government website. But something I point out is that say you get paid for, like, doing a terrorism, right? You're like, nice, no one can link these Bitcoins back to me. Then you're like, cool, I'll just go cash out these Bitcoins into US dollars at a bank in the United States. Don't do terrorism. Like, when you get paid to do a terrorism in Bitcoin, cash those out in some other country, right? Or, yeah. Yeah, you gotta make it harder on them, right? So anyways, some brain geniuses launched some cyber attack on the East Coast, asked for Bitcoin, and then apparently, like, cashed it out like 6 months later without transferring ownership. And yes, the FBI was there while they were cashing it out and took all of the money and all of the Bitcoin. So that's two things. But you know, game recognizes game. It's cool they shut down an oil pipeline, right? So timestamps are hard. They're actually impossible. This is a link to the Leslie Lamport paper that won the Turing Award for proving that you cannot determine what time it is. Speaking of time being hard, okay. This is what the blockchain looks like. You have a block. It contains various items. One of those items is the transactions. One of the items is the current time, so you know how recent the current blockchain is. And then the other items we will explore over time. You compute the hash of that, and then you put the hash of that in the next block. So you keep constructing these hashes over time. I'm not going to worry about transactions right now. I'm going to teach you graph theory, Merkle trees, and transaction trees next week. We'll have a good time. This is basically what a block looks like. It is the hash digest of the previous block. It is the hash digest of the transaction tree that we're learning next week. I had to do a forward pointer. I had to do one thing before the other. It just turns out this is an easier data structure, even though it contains the harder data structure. So that's why we're doing it this order. It contains a timestamp, and what is that? Time_t. It's an opaque pointer. We love those, right? Everyone in this class loves opaque pointers. Can I hear it for opaque pointers? We love to see it, right? And it contains a mysterious fourth thing. I wonder what the mysterious fourth thing is. It is the double spend presenter fruit proof of work thing. So how are we going to do this? we're going to say the first spend is authoritative, and we're going to timestamp everything. And then we're going to make it impossible to retroactively doctor records. And we're going to do that by SHA-256 hashing a whole bunch of stuff. And we're going to call that process Bitcoin mining, because the children long for the mines, right? They love Minecraft, so they love Bitminecraft. So we're going to put a mysterious fourth thing in our block, and it's the nonce, the number that is used once. It is the fourth field, along with the previous block, the transactions, and the time. How's this work? I pick a number, I compute the hash of the block. The hash of the block must have some number of leading zeros before any of the non-zero values start. And I know what you're thinking. You're thinking, it's probably easy to have one leading zero. Yes, you can probably compute 2 hashes and find it. And you're thinking, it's probably pretty easy to have 2 leading zeros. It's like, yeah, no problem. You only have to compute 4 hashes. And you're thinking, I wonder how hard it is to have 47 leading zeros. And it turns out you have to compute 1 times 2 to the 47th. I don't know why I started saying 1. 2 to the 47th hashes. And some of you have computed an SHA-256 hash on your computer, and you're like, this is a space heater, right? So if you do that 2 to the 47 times, it takes a while. And the way you change what the hash is every time is you change this number that is used once every time, right? And you try and change it in a way that you don't think the competition's changing, because you want to hash that thing first and you want to get paid for mining that Bitcoin. That's proof of work. It's hard. Here's an example where I tried to get something with a trailing zero. I never remember if it's leading or trailing zeros. I just checked the paper. It's leading, but I did trailing. So there's a 0 here. It took 16 tries to make out there's an F. This is DD transmission. And you can verify these with your own SHA-256 sum. Bitcoin has difficulty scaling. It is scaled so that a new block is created every 10 minutes, no matter how much compute power is being used on the network, so it gets harder all the time. They always aim for a block every 10 minutes, which is great. You swipe your card at Starbucks, then you wait 10 minutes. You find out your transaction was accepted, and then you waited another 10 minutes to see if it was actually in the next transaction. And then you're still not sure, because there could still be some challenges to the future blocks. So you actually have to wait until forever to know for sure that it was spent. But you can be relatively confident after it appears in a block. I think this is some political commentary. Right. The longest chain is the authoritative chain. This is a big deal because every once in a while, a server in Australia, which is difficult to get information to quickly, and a server in New York City both create a new coin at the same time, and they might have slightly different transactions in them. How do you decide which one's first? Well, the Bitcoin network is going to start working on the next coin for each of those 2 blocks. And eventually one of the chains will be longer. And that chain that is longer is the more authoritative chain. What this means is just because your transaction appears in a block, someday a longer chain could overtake it. Now, it is infeasible that a chain that is not very close to current overtakes it. So after you wait a few minutes, you can be confident you're in the authoritative chain. But there was, in fact, a permanent fork in between Bitcoin and Bitcoin Cash. And everyone that happened to have a Bitcoin before the fork has both a Bitcoin and a Bitcoin Cash. They have both currencies, and they get to spend both of them. But of course, this is baked into the valuation of Bitcoin and Bitcoin Cash, right? So this is unsurprising. It's not like anyone got free money for that. Satoshi Nakamoto claims that if the majority of the CPU power, because GPUs weren't used yet, funny we say that's compute power, as we're doing this on complete custom hardware now. The idea is you only participate in Bitcoin if you benefit from Bitcoin being trustworthy. So it is odd to participate in Bitcoin and try and make fraudulent transactions. A Bitcoin consortium got very close to controlling a majority of compute power, and they voluntarily split their consortium because as soon as one entity controls half of the compute power in Bitcoin, the valuation of Bitcoin goes to 0. So if you're a Bitcoin miner, you don't ever want that to happen, right? So everyone is massively incentivized to make this thing look legit. This is really bad for the environment. The Bitcoin network works as follows. New transactions are broadcast to all nodes. Each node collects the transactions and makes a block. They probably make the same block, but maybe they have different information, or maybe they have a different algorithm going. It is decentralized. Once you build your block, you start computing proof of work. If you find proofs of work, you release it to your network. You hope other people adopt the block, but maybe they find some problems with it. Maybe they find a fraudulent transaction you missed, right? So they don't start working on your block. You broadcast the block, and then you find out if your block is accepted. How do you find that out? Someone else makes a block after that block and becomes the longest chain, becomes authoritative. And that's what all of those things say. Bam, blockchain, lists that don't lie. See you next week. Thank you. Oh, look how close I was on the time. Oh, it's so. Incredible.
Two things, just like a follow up on my project. I was like a potential idea.
Oh yeah, how's it good?
Good. I was just looking at the slides from the first one I went to and looking at different things. This is like one of the things I was like interested in writing about, which is like or just that, which is like well, 5 Bitcoins. If that's cool, still if they run that,
Yeah.
maybe I'll want it or something.
Do it. Yeah.
And then it's let you know I might be late and I just have to be at the job next week.
Cool. I will have it up and I hope to see you. But if I don't, all good.
Sound good.
Thank you for checking in.